observe is researchers are mostly concerned about what happens to the yield of these catalysts. But there are only selected reports, if you find out, that tells you about how the catalyst behaves and to understand the mechanism by which this catalyst works. So some of the times, like when a very good activity is obtained, we just forget about the catalyst. We just concentrate only on that activity. But I think that the catalyst nature and how it is changing, that is important to understand here. One such thing that has come up is basically in situ measurements, which are actually the operando measurements. We don't do that because of lack of the facility right now, but that is one thing that we should go for. Yeah. So the first part, I'll tell you about the catalyst for battery part. Okay, now what battery we normally use? We don't use the lithium-ion battery. We don't work on that currently. And lithium-ion battery, it is used everywhere, starting from the laptop. I'm giving the presentation to our mobile phone and all the things. So we are interested right now on metal layer battery, and we started this research something like around 5-6 years back. And let me tell you briefly about the zinc layer battery here. And zinc layer battery is very much environmentally benign, and that's why we basically use it. So we have one side the zinc anode, the other side we have the gas diffusion layer. This is porous, and we have to allow the air to pass in. We cannot use the battery at a place where we don't have air, which is understandable. These are the two reactions which happen, and the total voltage, cell voltage, it is around 1.65 volts. Okay, and the electrolyte used is very highly alkaline, which is 6 molar KOH. Now there are two redox processes which go on here. First, when we discharge it, the zinc metal, it goes to the Zn2 plus, and oxygen goes to OH minus. We call it oxygen reduction reaction, and which is in short called ORR. The reverse process takes place during the charging, which is called OER, that is oxygen evolution reaction. And then here in the anode, Zn2 plus goes back to zinc, and OH minus goes back to oxygen, and then the air goes out. Now, for this process, as you know, the cell voltage is 1.65. So these black lines, the dotted lines, these are the thermodynamic potentials, okay, and this is something like 1.65 volt. But we know that when we charge the battery during charging, the blue lines here, we need more voltage, and we need more voltage greater than 1.65 volt. Okay, and when we use the battery during the discharge, we get less voltage than 1.65 volt, which is not a very good thing. So because of the difference, this part is called the overpotential. Okay, from the blue line to this orange line, this part is called the overpotential on the cathode side, and this one is the overpotential on the anode side. So we have to reduce the voltage during the charging and increase the voltage during the discharge, and the overall process is to minimize the overpotential for both the processes, which is oxygen evolution reaction and oxygen reduction reaction. For this purpose, we have used the first two case studies. I will tell you about the perovskite oxides, and these are basically AbO3. These are cubic structure mostly, and A cations they sit on the corners of the cube, and the B cation, the blue ones, is at the center of the cube, and the face centers are occupied by oxygen. Okay, and these are mixed ionic and electronic conductors, so they are highly useful, and we can tune the physical properties by doping at A and B side, and they have very stable crystal structures. Now we can basically change these things. We can actually dope at the A side, we can dope at the B side, we can choose the morphology, or we can choose the elements that we want to have at the A and B side. Now these things basically control here, that is the crystal structure, electronic states, conductivity of the system, and oxygen vacancy. For the electrocatalysis, for a catalyst, conductivity is a very much important thing. And all these factors, they govern the catalytic activity. So it is an overall process, and you can understand that the richness of the chemistry which is involved with this kind of systems which are perovskite oxides. Okay, for the solar cells, it is the halide systems which are used and which have really gone up like anything. But for the electrocatalysis purpose, it is the oxide system, and you can easily find out the redox processes by in this kind of materials. Now for a perovskite oxide, what happens is in an AbO3 system, B site is basically the active site. So if you make a 2D structure, two-dimensional structure, if it is terminated by the B site cations, your reactants can easily adsorb on the surface and you can get the product. Okay. Now, if your surface is terminated by the A site, probably it is not the case. I'll tell you in the next slide. Now, the B site, it is highly controlled by the EG orbital occupancy. If it is singly occupied, that is one electron is there in this the EG orbital of the B side, then we have a facile reactant binding and charge transfer which takes place. For the reduction, electron is transferred to the reactant. For the oxidation, that is OER, OH minus basically transfers the electron to this side. So singly occupied EG electron is important here. Now, if it is A side, OH minus cannot do the job. Now, what we can do here, if it is A side terminated, we can reduce the oxygen coordination over the A side. Okay, and if we can do that, we have some kind of oxygen vacancies which we create on the surface. So you see the white, you see the red ones, and we are creating oxygen vacancy here. So it has become white. The red part is very small, and because of that, it becomes active. And here this OH minus can then bind to these kind of centers, and then we can still run the reaction. But of course, A site cannot be as active as the B site, but we can still make it work. Okay. My main thing here that I'm going to tell you in the first study is that we have seen that with a redox bias, oxidation and reduction, electrochemical oxidation and reduction, the catalyst surface changes. Okay, there is a reversibility of the surface in terms of oxygen vacancy. That's what I'm going to tell you, and let me keep a note here that this is not observed usually, and this is a very rare observation that we have got here. So let us see how we did it. My recently graduated PhD student, now he's a doctorate, Dr. Rahul Maji, and most of the work that I will show is basically done by him. So he has done this. So first, here the A site consists of 50-50 of barium and the praseodymium. Barium is 2+, praseodymium is 3+, manganese is 3 and 4+. So there, because of the cation misbalance, there is some kind of oxygen vacancy. This the delta comes in. Now this AbO3, this is A, manganese is B, this is O3, okay? And this is called a single perovskite. Now we made that. Now this is a mixture of two different crystal structures. One is orthorhombic and also hexagonal. So there's a mixture of these two. Now what he has done, he has reduced it at 750 degrees C in the presence of hydrogen. And once he has done that, you see this 0.5. So this is BAPR, this is at the A side. At the B side, it is B2, that is manganese 2. And O3 multiplied by 3 multiplied by 2 is 6. Okay, but what we observe, it is not 6, it is rather 5. So 5 plus delta, that means there is enough oxygen vacancy there in this system. Okay, now when we do that, oxygen vacancy, when it happens, oxygen doesn't come out from this manganese layer, but they come out from the PROX layer. You see, it has become vacant. This was the PROX layer. This has become vacant now. So oxygen doesn't stay there. So you can basically shuttle oxygen to and fro. Why this happens? At the PROX layer only. Praseodymium has a smaller radius, okay, than Ba2+, and oxygen vacancy can only change its coordination at the smaller cation. That is much more easier than to do it with a larger cation. But both are isoelectronic in structure. Now, the next thing that we have done, we have doped cobalt at the B site. Okay, so manganese we have replaced with cobalt, and when we have done that, we have varied the cobalt concentration. But if we increase it too much, we have a lot of impurities here. I don't want to read out all this. There are a lot of impurities, but we have seen that at 0.25, that is, cobalt is 12.5% doped. So 0.25 cobalt here, it is the best. Yes? Yes. Okay. Am I audible? I hear some sound there.
You're audible, sir.
Thank you very much. Yeah. Okay, so by the Bragg's law, you see that the peaks, the 2 theta peaks, they basically shift towards higher angle, and that means there is a shrinkage of the unit cell volume when the cobalt goes inside the system. All right, how they look like. So making 2D structures of the perovskite oxide, remember these are not layered perovskite structures. Layered perovskite structures have a 2D structure, but when you have an AbO3 whole N type of structure, then you normally do not have a 2D structure, but we could make it as a 2D structure by making the perovskite multiplied by 2, the unit cell multiplied by 2, that is the double perovskite. Okay, so we see that the sheets are basically stacked on each other and they are highly crystalline, and one side here it is double, the other side you can see that this is 1 by D, okay, and this is D. These are very basic things, let me not go into that. So what we find out is these are the thickness. So the typical thickness of the sheets are 4.1 nanometer. And if you stack them and you know what is the height of one unit cell along the C-axis, you can divide 4.1 by that unit cell length, and you can find out how many unit cell thick they are. And what we have found, they are 5 unit cell thick. Every nanosheet, it is uniform, 5 unit cell thickness. Now I come to the reversibility. Okay, now you see that when you oxidize the sample means you are supplying more oxygen. So oxygen, you see the red fraction here, the red fraction has become more here. So you apply a positive electrochemical bias, so 5.06 becomes 5.16. This change is very slight, but we could still observe that. Okay, and when you reduce it, this goes back. And we have done oxidation reduction cycles in the neutral electrolyte first of all, and we have varied the number of cycles 20, 50, 100. Now we can do first oxidation, then reduction, then oxidation. So we can do one after the other in this way and scan it between 0 to 0.8 or 0 to minus 0.8 volt. Okay, now when we do 20 redox cycles, so ox 20 means 20 cycles, ox 20, red 20 means 20 oxidation cycles followed by 20 reduction cycles. Now this is again after the reduction we have done oxidation, and this is after that reduction, and so on and so forth. So when we do that, what we observe, you see this this yellow highlighted part, there is a peak coming and it's going away. Okay, this peak is coming, this is the PRO 1.8. There is a secondary phase which is coming, and this is very unique in the sense that a secondary phase comes out during oxidation. Okay, you see the hump, and during reduction it gets dissolved back into this perovskite lattice. Okay, so and the surface we have seen that it is highly combinated with PR here by the mapping, and so this is possible. But remember, PR is here a A-side cation, it is not a B-side cation. And if you look at the selected area electron diffraction patterns, you see during oxidation, you see this extra, the spot, the diffraction spot, which is due to the PRO 1.8. After reduction, this is gone. This spot is gone, and then it comes back again. It comes back again. So it is actually reversible, and this is more clear and this is more evident when we do 100 cycles. You see, when we do the pristine sample after 100 oxidation cycles, the peak has come up, reduction cycle is gone, after oxidation it has come back. So during oxygen coming in during oxidation, there is a lattice expansion. What is taking place? You see oxidation, there is a lattice expansion. During reduction, there is a contraction. So this is a to and fro process of entry and exit of oxygen at the PROX sublattice. Now we have changed the electrolyte, and we now do it for this OER to ORR to OER, this kind of process. And we can also do first ORR, then we do OER. So first reduction, then oxidation, reduction, then oxidation. So whatever we do, we see that this kind of expansion, contraction, expansion is taking place. Expansion only takes place when it is an oxidation. Contraction of the lattice takes place when there is a reduction. But when we start with this oxidation first, there is a structural robustness of the system, so the reversibility is less observed. But when we start with the reduction process, it is better observed. Okay, so that's what we have done, this redox cycling activities. This is for the oxidation, this is for the reduction. They are not very good, but because the surface is terminated by the A site cation, catalysis is taking place only at the surface. But this is a very unique demonstration that oxygen coordination of the A site cation is responsible in influencing the catalytic activity, and it's not the B site actually. Now further, we have improved it in another work where we have coupled this nitrogen CNT with carbon nanotube. I mean, these are basically the functional groups on the surface with this, the perovskite sheets, and we see there is a very good connection in between the perovskite sheets and the carbon nanotube. And we have varied the concentration. These are the zeta potential. We see the surface charge becomes more negative when we increase the carbon nanotube concentration. So what happens here? There is a p-n junction which is created. So the carbon nanotube is n-type, and the perovskite nanosheet, it is p-type. Okay, and there when we change it, we have done a mod shot measurements, and we see that the Fermi levels, they basically change, and these basically goes up. Okay, this has to go down and this has to go up. Then only you have a better electron transfer process which can happen here. Like if this is shifted up, you have a electron transfer process, this is a reduction, and this is the oxidation, it is shifted down. Now, when we have 10 weight% of the NCNT, the combined over potential, that is a extra potential that we do not need, but it is inevitable, that we have brought down 2.79 volt, which is very nice. Okay, so there is better oxygen activation in this case. So after this study, let me go to another one. So the surface, when you have a solid state material, you also have the grains, like these are the grains, you have the grain, the boundaries on the surface. So these white regions, these are the grain boundaries, and they're not so nice to have grain boundaries. These are the defects or defective regions, and because they are non-crystalline and they are minimally conducting. Perovskite oxide as such is not very much conducting, but grain boundary is even less. So it impedes the catalytic activity. So one way to do is that we introduce a noble metal particles along with this oxide system, and so that they have complementary catalytic activity. Like if we take palladium nanoparticles and we put on this. So we take this perovskite system. So the A site contains lanthanum and strontium, B site contains the cobalt, and there is a partial doping of palladium 4+ at cobalt 3+ because of nearly similar ionic radii. And when we do that, we can have this complementary activity, that is the perovskite oxide, it facilitates oxidation, and the palladium, it facilitates reduction. Okay, so we can do that. And this is the system. You see the grain boundaries are there on the surface. These are transmission electron microscope images. And when we do a mapping and of this, we see the palladium, only the palladium, it is sitting over the surface. There is an increased concentration at certain regions. It is not uniform. The palladium, it is not actually uniform throughout. That gave us to this idea to study that why not we find out the D-spacing. Now we found out that interplanar spacing on the grain, it is less, like 0.280 nanometer. Now when we do at the grain boundary, this is going up, but in the third the decimal. Okay, so that means there is a increase in the lattice volume at the grain boundary than it is at the grain. So there we can say that because palladium has a slightly larger this ionic radii than cobalt, so it can increase the lattice volume. Okay, so excess doping gives rise to increase in D-spacing, and that can increase in the lattice volume. We found out one equation ourselves. We also did not know whether it is correct or not. Reviewers have not commented on this, and so I am showing you here. So the defect percent that we have found the D at the grain boundary, the interplanar spacing at the grain boundary, minus that at the grain divided by the D spacing at the grain. And when we have done that with different concentrations of palladium, okay, we see that when the palladium, this is 3, that is 3%, we see that it is the maximum. So the defect percent is maximum, it is 1.29. Okay, that is percent. So this has the highest defect in the system. Now with this system, we did both oxidation and also reduction. And when we did that, we observed a very unique relationship with the defect, as you can see here. This is the combined overpotential for oxidation and reduction. So if the overpotential is lower, it is always better. Okay, so this goes down, and where it goes down, where the defect is, that is maximum. So here, the grain boundary defect at the surface, it helps in increasing the catalytic activity. That is the message I want to put here. We have made zinc battery by this way with Teflon electron chamber and zinc foil. This is the anode and this is the cathode side. I'm not going to tell you about the zinc battery thing. If you are interested, you can ask me afterwards. I can tell you. I have to move on because the time is short, so I will move on to the next system, which is water electrolysis. Very much widely researched, and it is worth researching. It all depends on how good a catalyst we can make. Now, you can see that the oxidation reaction, which is oxygen, the evolution reaction, OER, it involves 4 electron process, and hydrogen evolution reaction, HER, involves 2 electron process. So it goes to an activation energy barrier. If you apply the catalyst, this barrier will go down, and you can easily go from the reactant to the product side. Okay, you can do it both in the acidic medium and also the basic medium, and these are the reactions. These are the textbook things which can always be found out. Okay, so here we are doing water electrolysis. Our aim is to use catalyst nanoparticles, and we avoid noble metals, with which we use catalysts which are cost effective and which have good performance and also stability or durability, whichever way you call it. This is the anode where oxygen comes out. This is the cathode where this hydrogen comes out. Okay, the first system that I'm going to tell you is the heterogeneous alloy. So why it is heterogeneous alloy? Because the miscibility of these two metals, silver and nickel, they are very less. They cannot create solid solution with each other. because the miscibility, the crystal structures are widely different, and the ionic size is also very large. The difference is large and so on. But we use the non-aqueous heat-up colloidal reduction method, and here we use several surfactants like phase transfer agent, this TBAP, and we use this oleolamine, co-reducing agent surfactant, dodecandiol is the weak reducing agent, this oleic acid as a surfactant. We made this, and finally, since we have nickel, it is actually magnetic, so we could separate it with a bar magnet, and every reaction is done under the inert atmosphere, Schlenk line. Now what happens, as I told you, there's a large lattice mismatch by 14%, and there is a miscibility of the metals, and the silver radius is larger than nickel, and so when you put silver into the nickel, but not a very large amount, a very small amount, like these are the amounts which we have put, 1.1, 5.5, 10.4 and 26.4, we see that there is a shift towards the lower 2 theta here. So that means some amount of silver is going into nickel, which is not supposed to go, but because of the synthesis methodology, it is going, okay, but entirely it cannot go. So there is a shift towards lower 2 theta, and so the lattice is going up because the size of silver is more than nickel. And by refinement, what we found out, there is no only nickel, only nickel impurity. Silver is there, but 85% it is nickel-like. It is not exactly nickel. 14.4% it is silver-like. It is not exactly silver. Means some amount where it is nickel-like means small amount of very small amount of silver is there. All right. If it is silver-like, a small amount of nickel is there. So it is a different phases that are formed, and there is 0.6 weight% of metallic silver impurity, but it is quite small, less than 1%. Okay, it is a face-centered cubic structure, and that's what we found out. Let me tell you about this electrocatalysis first. We did the reduction process, which is hydrogen, the evolution reaction. You see, this is platinum. Platinum is a very well-known HER catalyst, and it has an overpotential which is 20.1. I repeat here, lower the overpotential, better the catalyst. So for this 5% silver, 5.5 weight% silver, you see it is the overpotential is 24 millivolt, matching close to that. So comparative HER activity with platinum, not many catalysts actually show that. Okay, and pH universality is also there. That's what we have seen, and the turnover frequency is 2.1 at 50 millivolt overpotential. The Faraday efficiency is 99.4, and it is stable both in acidic medium and also the basic medium. Here the current is going up because it is negative, so it is not going down. Now let me come to here that how the surface of the system is, this electrode is. So only nickel, you see it is spherical, okay, but as you increase silver 1%, 5% and so on, the shape is changing. So the shape here, it becomes a dodecahedron. Dodecahedron is something like this. So this is with 5.5 weight%. Now what we found out by point TDS analysis, we put points in the TEM, and we found out that the edges, like if I go back here, the apex, this is the apex, these are the edges, okay, exactly what we see here, this apex and these edges, they are more silver rich. Faces, that means these faces, okay, they are more nickel rich. That's what we found out. And if you see at position, this is the apex, you see the amount of nickel is much lower, silver is the much higher. If you go to the faces and so on, it changes. Okay, so there is a selective occupying of the positions in this structure. So nickel is HER active, silver conductivity is more than nickel. If the silver is concentrated more at the apex and at the edges, it exposes more HER active nickel on the surface. So that's how when the active sites go, it will increase, the surface of the catalyst becomes better, and this HER kinetics also becomes much better. All right. So this is one system. And silver also does another thing, that it reduces this oxidation of nickel. So it will stabilize the nickel 2+ state. It will not allow to move to the 3+ state very easily, because if you increase the silver amount, you see the potential for this oxidation, it moves towards the higher oxidative potential here, which shows that if you do a CV cycles, you will easily understand in the system whether it is more easily it is getting oxidized or less. So if it is difficult to get oxidized, then this oxidation peak you will observe at a higher potential. So with silver, it actually prevents nickel 2+ to get oxidized to nickel 3+. Okay, this is the last part of my talk, and this is about a catalyst surface, but it is deposited on a self-supported and flexible electrode. Flexible electrodes are very much important. You see, it doesn't change the surface, but if it is not flexible, if you bend mechanically, it is not robust. There are a lot of cracks and other things which form, and this is not so nice for a long-term electrolysis. Okay. Here, my PhD student, she's in her final year, Shahnaz and Ashwini, he is now doing PhD abroad. So they made this catalyst. They started from a very unique copper mesh catalyst, and they grew over it copper hydroxide wires. They electro-reduced it, made it copper wires, and then again it did the electro deposition and created the layers of nickel cobalt layered double hydroxide. So this is layered double hydroxide which is created on the wires. So you see the surface area has also become more, because this all the reactant can enter through all the sides. Okay, this is the TM image of the wire. Okay, this is this LDH. You can see something is here on the surface. If you zoom in and if you see there the lattice fringes, you see this is for the LDH and this is from the copper wire. Now, before I go ahead, let me just show you the result here. If you do not want to look here, a lot of catalyst systems, just look here. This is platinum. This is nickel cobalt LDH on copper nanowire. So what is happening at 10 milliamp per centimeter square current density? Platinum is 22 millivolt over potential. This is even lower than that, okay, which is do not observe very easily. At 100 millivolt, okay, at 100 milliamp per centimeter square current density, platinum is around 97 and this over potential is 72. So over potential is much better. So we can have a very earth abundant catalyst which can replace platinum. All right. So you see that the current density actually goes up, and this is the platinum line. The TAFL plots show that the kinetics they are at par with each other. So this is more platinum-like. And what is happening here? So Dr. Ghosh, she was a postdoc, but she's still working many of her research about the partial density of the copper atom and different d orbitals. What she observed that when it is a 3D structure like copper mesh, the Fermi level is much, the much away from the Fermi level. But when we make a one-dimensional structure like this, so it moves towards the Fermi energy level. You can see here. So the partial density of state of D level and the Fermi energy level when we have nanowires. And what it allows the easy transfer. If it so the mesh is never, when you make that, it is actually finished. And you see the pH, actually our electrode worked better than platinum, frankly speaking, at here, in all the cases. And these are the turnover free frequency, 0.3 and 0.32 at pH 14 and 0. That's what we have seen, the turnover frequencies. And if you look at the stability, you see that at very high current density, there's very stable. This is around 1 ampere. So this same thing is here. It is around 1 ampere. You see it is constant. It doesn't move. And these are different electrodes, 5 electrodes where these overpotentials are kept here. And this is highly reproducible, 15 millivolt plus minus 6. So it is quite good. Okay, I have shown you a few catalyst systems and the surfaces of these catalysts. And I hope I could give you a picture of this, how the catalyst surface is important and how we actually work on that. And so these are for the batteries that we have done this, and this is for this hydrogen towards that. And these are the shaded, my students, they have all worked on these catalysis. They are working, rest of the people are working on something else. So it is quite like many people are working in this area. Yeah, that's what the thing is. So thank you very much.
Thank you, sir, for your magnificent talk. The session is now open for questioning purpose. If anyone possesses any question, you can unmute yourself and ask the question.
Yes, please.
Yeah. Can I ask?
Yes, you may proceed.
Yeah, I think a lot of noise is there. A couple of questions. This is Rangarao from IIT Madras. Can you hear me?
Yes, I can hear you.
Now, quick question is, how did you estimate oxygen stoichiometry in your compounds? Because you are showing precise numbers.
Hear you very well. A lot of noise actually.
Yeah, a lot of noise.
Let me stop this, baby.
It is better now?
Yeah. Please tell me.
Yeah, you have been giving a very precise oxygen stoichiometry numbers in your compounds. How did you estimate those numbers?
Okay, this oxygen, there are many ways that one can do is, we quit first of all by the visual analysis, and we match it two samples with the CHNO analysis, and also the titration by which we can easily find out that.
Because the other error bars
Sir, can you just repeat it?
Yeah, I was just wondering. There could be some error bars, in your measurements.
No, these whatever these oxygen numbers that I am showing here, there are of course the error bars. You are absolutely right. I am not showing them here to keep it very simple. But of course, when we say it is 5.16, it may not be exactly 5.16 plus minus something. Okay, but I'm not showing that here. But consistently, to make it sure, and this is the question actually everybody will ask, that is how you are sure that that is the exact oxygen amount. So we have done analysis at least for 5 different samples, and we have found this is the mean, and the difference that we see is very less. And that's what we have done. And we have done oxygen estimation by many ways. But one that we have done is definitely by that read well analysis.
Yeah, so there are many questions, but anyway, let me congratulate you. It's a wonderful piece of work.
Thank you. Thank you.
Maybe I will get in touch with you later. Thank you.
Thank you, sir. Thank you, sir. Thank you. Are there other questions?
Hello, can you hear me?
Yes, of course, I can hear you.
There is some issue with our WebEx. There is some echo.
Maybe other have to unmute as well.
Yeah, now.
Yeah, your voice is cutting. I can mute myself right now. Any questions? That's what.
We're facing some technical issues. Any more question on the board? I guess no. Thank you so much, sir, once again. Thank you so much, sir, for being patient and considerate. We shall now move on to the next talk. We have with us Dr. Vijay Narkare, who works as the Research and Development Manager at Chemi India, Gujarat. He is a skilled research science chemist with a doctorate in heterogeneous catalysis, having academic as well as industrial background. He has sound understanding of catalyst preparation, process chemistry, characterization and catalytic processes, and a deep expertise in designing and validating catalyst architecture for its economic viability and feasibility. He has published more than 20 journal articles, 3 patents, and a book chapter, and has more than 1,000 citations. I now request Dr. Vijay Narkare to proceed with his talk. Thank you.
Thank you very much for your nice introduction, and just please allow me to share my PPT, because so far I couldn't see there is a permission to share.
All right, sir.
Yeah, I mean, there is no activation of the shares here, right?
So we are having some technical issues. We are going to resolve this soon and let you know. So just bear with us for a few minutes.
Yeah, okay. Now I can share it. Oh, no problem. Can you see, please?
Yes, sir.
Okay, good. So maybe you can unmute so that you can others can hear. Okay. Just first of all, thank you very much for invitation, and I'm really glad to see a lot of very deep fundamental stocks are there, and this is Okay, I'm going to talk more on application base, which whatever the current problems are in industries, how we work, and other things. But I thanks Professor Varali for inviting me, and it is really a very good, I think, platform to share our work and discuss the catalytic issues that is going on in the current way. So this is my talk is going to be a very different one that what you could have here so far, and this is a really on industrial processes. And the like in automotive catalyst, this is a very old subject, but still there are a lot of challenges. And in India, we do face a lot of air pollution problems, and there are still a lot of way to go. This one, this is just to give a brief introduction of my industry here, like in Sudkemi. We have a two unit. One is in Baroda, another is in Kerala. So here, basically, what I'm showing is a main gate, and then here you could see the you have this quality as well as the R&D departments, and this is something we have the testing department here. So just to this is a content of my talk where I will introduce you what is really air pollution means and what are in India, because this is this is a presentation I prepared specially because there are a lot of people from India here, so better to talk what is really the current scenario in India, what are the emission norms in with different respect to like truck, buses, on automotive industry. So there are many different technologies has been applied to meet the norms, like three-way catalyst, diesel oxidation, and I will talk a little bit, a very brief on each of them, and then summarize my talk. If you look, what the WHO is saying that okay, there are more than 7 billion people, or sorry, 7 million people are dying every year almost because of the air pollution, and this is what they refer as the silent killer. If we see here in this map, the India is the worst heated country in the whole scenario. So really, the quality of our the quality of our air is very poor basically. So that is why one of the program Indian government has started is like the National Clean Air Program, and here a lot of also I think there are a lot of projects also they fund to different universities and different institutes from this kind of program. And particularly for this, if you look at the particulate matter 10 and 2.5 and 10, so there is a lot of different problems. And if you look at the air, normally how much air and food quantity and how much water we drink every day, we can see that there is almost the major part of air we are breathing almost 11,000 liter every day, and this is really huge one. Okay, and even the athletes can breathe much more than what we can, almost double we can say. So here, what are the sources for the air pollution? Now you may see there are there are different categories. This is from Wikipedia basically, but you can see that there are the 45% is basically coming from the dust, with the construction dust, lot of dust particles, because this is basically again for particulate matters that we are talking about, like 2.5 or 10 micron particles. Then another thing is coming from the waste burning, then automotive, and then there is another area which is industrial pollution, again domestic cooking and other things. So there are a lot of different issues and their different technologies are needed, though I will not be able to cover each and every part of it, but automotive, where the transport basically 14%, but we will see that how we can really make the justice for this one. So if you look at the vehicular emission regulations, this in term of a regulation, Indian government has several regulation type, basically in which one of the thing for mobile application only, which mobile means which are really moving on the road and how much they are being controlled, like CO, methane, or even methane separately, and then non-methane hydrocarbon, that is again separate criteria, NOx and N2, though it is not so far regulated, but it can be a future one. Again, NO2, though it is also not directly mentioned, but yes, it is indirectly, it covers that one. Then ammonia, yes, it is covering in particulate matters, and CO2, again, this is going to be a future one. So everything, these regulated gas components will be covered in future, or currently there are going on. So now in whole India, we have all petrol, diesel are less than 10 ppm sulfur containing fuel available, which is a regulation for BS6, which started from April 2020 only. So just you can say 1 year back. So here, like two-wheeler, three-wheeler. So depending on the different categories, these emission norms are also different. Two-wheeler will be different. So whether which fuel type is using, how much is the weight of the vehicle, whether it is off-road or on-road. So there are a lot of categories also. Depending on that, they will be covered. If you look at the scenario in India, we have almost 30 million vehicles are produced every year, and out of that 80% we can say is two-wheelers, and then again 4% and three-wheeler and commercial vehicles also four-wheeler, and these are passenger vehicles which are 30%. So this is the kind of production scenario in the current. This is the data from last year data taken from SIAM. So in brief, if you look at how the Indian emission regulations has gone, like from 1991, India has started the controlling the air pollution, and there are regulations. But here there was no catalyst needed from 1991 to almost we can say 1996 or even 1998, because this can be only done by the engine management. So how the engine is being tuned, like air to fuel ratios, and there are several parameters even the mechanical engineering can do. And then later on, then there are different kind of like Indian driving cycle, and then in particularly only in some area it was implemented. Later it was again implemented with some CNG LPG vehicles. So then step by step, we in 2017 we went in Bharat Stage 4, which is almost in some part it was regulated, but from that time whole national wide it was implemented, like BS6 on the same day, we can say 1st April 2020, on whole India, all vehicles should be should have like BS6 approval. Otherwise, they will not be able to solve it. So there is also future, and there is lot way future to go. In fact, here there are OBD2. Whenever there is a catalyst is failing or some malfunction is happening, there will be a mill light on your text, so that you cannot run vehicle further. So what are the different technologies is being utilized for this kind of to meet these emission norms, to fulfill the government regulations? And this is how the metallic monoliths are available, ceramic monoliths are also available. And these are the diesel particulate filter, which are basically on one side the holes are blocked, and another side also the another vehicle the channel will be blocked. So what that blocking means is like the gas has to pass through the wall of the ceramic, so that ceramic wall can filter the particulate matter. I will come to that point, show the better figure than this one, but just on this, like if you coat the or if you have how you put the catalyst on it, this monolith are coated, and we can see here there are some thickness, and we can say there are multiple catalysts can be applied on these monoliths in a layer wise. So these are some real pictures of the catalysts that we produce. Just and simplified before I go, show you example of three-way catalyst and how the regulation means really. So in three-way catalyst is a closed system where the engine is there, we have air inlet, you have fuel inlet, and this is again, it is managed by the small computer, you can say within the vehicle is engine management system. Then we have oxygen sensors, which are really needed for catalyst to function. Without this oxygen sensor, the functionality of the catalyst will be a big question mark. So this is a very simplified diagram where we can say, yes, these are the, because catalyst here doesn't work independently. It is integrated with the total engine management system. And then with the oxygen sensors, all their feedbacks are needed to function the catalyst. Here, there are some parameters here. I can say, like, engine size. What is the size or the class of the vehicle? How much engine? Like engine size means when we say there are like in two-wheelers, you can say 100 cc vehicles or 250 cc vehicles or like depending on how big size is the engine, which classes it is coming, how much catalyst is needed, how much quantity we have to put, and what is the specification of the catalyst, what is the position in terms of how long it should be fitted from the engine. And again, these lambda variations will be always there. There is a misfire again. So all these things are really important to consider in terms of a catalyst. And these catalysts are really, needed to be robust because I will show you the temperature, what is the range it is needed basically. So this is the general setup it is needed for testing this vehicle. This is a facility Sutkemi has available in Baroda unit, and like let us say this is a two-wheeler fitted on chassis dynamometer, and the person is running in a real driving cycle. That driving cycle I will show you in the next slide. Here, suppose this is a muffler, and in muffler you can see this is the catalyst here, there is another catalyst here. Depending on the regulations, the number of catalyst can be different one. So these are the very expensive facilities are needed for measuring all the emission regulations, and these are the typical reactions that we look at it, but this is not a limited one. In a brief, we have various components working together. We can say there are multiple number of hydrocarbons are available. Even we can find a methane C1 to even up to C10, C12. Also, there are some kind of molecules are available. So this itself is a very big area. Even CO, and there are many combinations we can make out of it. So overall, more than 200, 300 type of reactions can happen at the same time on this catalyst. And we have to look at each elementary step of this catalyst. So though it is not going to be part of my talk, but just to brief you that this is a very complex system, though it looks the very old study, but still there are a lot of challenges. So the wash code designing, wash code basically is a kind of catalyst powder with a coatability, like we can say like a paint. It has to be like a paint so that we can coat it on the ceramic monolith, or it is a metallic monolith. And they do have different type of systems. I mean, the substrate itself, there are many designs are available. So each reaction need a different functionality that we, as a catalyst person, we can really understand that like a CO, hydrocarbon oxidation, these mostly the platinum and palladium can be considered. Then rhodium, which is again NOx reduction, that is one of the main components basically. And then Syria zirconia type of materials are being used for as in the wash coat. Also the alumina powder. Yesterday we had a very nice talk from Professor Gurnat. I think he has also covered some points. So this is almost in a similar line, but a little bit on application side as well. This is the worldwide, this is the worldwide harmonized motor emission test cycle. This is how we run this test and to check the emissions, that how much milligram per kilometer CO is emitting from the vehicle. And that has to be measured with this specified driving cycle. And this driving cycle, like let us say when we start the vehicle at zero time, that means the temperature of the vehicle has to be also like 23 degrees Celsius. So when we just start, and then this is again, we have to also make sure that at that temperature also our catalyst is active. Now it is not possible to have a catalyst that is working, let us say, for hydrocarbon or CO oxidation or NOx reduction, working at really, just at room temperature. And this is how I would say the cold start challenges, available in market point of view. So, another thing, this is a cold start problem. And another thing is a high speed. At high speed, you may reach the catalyst temperatures almost 1000 degrees Celsius sometimes, depending on how the catalyst, where it is fitted, how it is fitted, and other things. So that means what is I'm talking here is the catalyst working range is from, let us say, from room temperature to 1000 degrees Celsius, and this is how the catalyst needs to be thermally, hydrothermally stable, and it has to perform even this is such a wide temperature range. And these are the really big challenges for catalyst development for automotive industry. I would like to give here just one typical example of 100 cc motorbike. Okay, so here if you look at the what are the BS6 limit that government has defined is milligram per kilometer emission. If you look at the CO is 1000, and then hydrocarbon is like just 100 milligram, and then NOx is 60 milligram. And if obviously this is not the final regulation in a term of like, if you say, okay, this is meeting any time, any catalyst can meet this one. But again, we have to look at the durability. Durability in term of, can one has to guarantee that after 20,000 kilometer, or even in term of cars, it is 160,000 kilometers, our catalyst is still functioning and still the limits are met by the catalyst. So this is also kind of a challenge, is that how long the catalyst should be durable. Now, coming back to this example, if you look at this, the vehicle itself is emitting like 1500 milligram, and CO, and 346 is like hydrocarbon, and then NOx is 256. So we have to come very low numbers to meet this regulation. And with the BS6 catalyst, you can see that how much reduction we have here is like 88% conversion efficiency, hydrocarbon is 90, and this is 97. This is exactly the conversion efficiency we need to calculate on the vehicle by testing. This is real data. Just to give you a brief that once we say yes, our catalyst is working and this one, but there are not only catalyst is functioning, the vehicle management or the vehicle or the engine developers are also working on it. Earlier, the air to fuel ratio was very wide, in the wide range here. And if you look at the modern EMS system, which are, they are narrowing the band between the variation, because, some people like to have a very high power bike and some people want to have better fuel economy. So each and every requirement has an impact on your engine development as well, and that has an impact on our catalyst performance too. So this is the TWC, how the three-way catalyst of our gasoline, how it is really functioning. So the next part of my talk is, I'm going to talk on the heavy duty vehicles, which you can imagine of, truck and buses and higher engine, which are maybe more than 5-liter engines. So here there are multiple catalysts in a series are needed to be, developed and needed to look at their integrity. So we cannot say, okay, I have one catalyst and it is working on that one. So it has to be integrated on the whole system, and like a diesel oxidation, or there is a diesel particulate filter, then SCR catalyst, and then we have like ammonia slip catalyst. Whatever the ammonia is getting emitted from this, it has to be well oxidized. So obviously from where the ammonia is coming, it is we are dosing urea solution, and which is giving for to convert a NOx to meet the regulations here. Now, we'll go one by one. That the diesel oxidation catalyst basically is again designed for CO and hydrocarbon oxidations, and again it has not only that function. It is also designed for the controlling the NO2 formation, because the NO2 formation is needed here for DPF functioning, and that is why the DOC has a three type of function to work, like hydrocarbon oxidation, CO oxidation, and NO2 formation. NO2 formation. So accordingly, based on the space velocity, based on the reactor design, in terms of how we where we feed the catalyst, that is basically again reactor designing, how big catalyst should be, or how each lengthwise how big it should be. So all these things are very, very important for designing the catalyst. Again, these are the typical curves for NO2 yield. We can say again almost 45% yield is needed. This is I'm saying 45% or 40%. That is not to be taken as a as a final value, because sometimes we need a even lower, because we do not want extra to be emitted in the air, so we have to control that NO2 formation as well. But these are the, again, when I say 60 gram per cubic feet, this is depending on the size of the catalyst. This is a particulate filter where, the particulate filter, there are two things basically here. As I earlier said that, okay, here we have the channel which is open here and then close here. So all the gases has to be passed through the wall. So the wall the wall is very porous, and the porosity is also depending on the design of the DPF material. So there are carbides or there are ceramic, means cordite or titanate. There are different type of materials are coming, and again as this DPF also has to be has to be sustained at very high temperature. It is not that again you can burn it easily. Even there are ceramic, but the temperature sometimes can be very, very high in the vehicle. So we have to look at that possibility also. And yes, we can, with the DPF, we can meet almost 95% particulate matter we can control, and they are normally they are giving more than 90% conversion for meeting this kind of particulate matter. When we have, let us say, a catalyst on that particulate filter, so we can coat also the particulate filters with the catalyst, and because let us say these are the kind of soot deposited on this material, and it is depending on the temperature, depending on the how much loading it has, so it will burn out. If you can look at that at 360 degrees Celsius, it takes hours to get oxidized, and if you look at the 600 degrees Celsius, within a fraction of minutes it can be it can be burn out. But again, the temperatures will be very high here because we have to look at the exothermicity of the soot. So overall, the temperature can go very high, and that is why we have to look at how much soot formation should be deposited on the diesel particulate filter, so that it can be also the exothermicity need to be very well controlled during the design of the overall catalyst. So when we say there is a soot is deposited on that one, then there are two ways we can burn soot. There is a NO2 or oxygen. When with the oxygen, it takes a lot of high temperature, and it takes higher longer time to burn out. But if we have NO2, it can be at low temperature it can be done, and that is why the DOC needs to be that is why people wants to have that DOC should form NO2, so that it can the soot can burn at low temperature. There will be no issues of other misfiring and other thing. So overall, what we need is the oxygen storage capacity for this one, because again the Syria zirconia type of material can be deposited, which can easily give oxygen, active oxygen to the and to that active oxygen can take part to burn the soot. And the NO2 formation, yes, it can do at low temperature. Sometimes there are other technologies are available where people are dosing directly the hydrocarbons, and that can also be possible. And also sometimes the hydrocarbon trap also can be used for controlling such events. And this is a kind of a selective catalytic reduction. Here, this is a very well known. Again, many people have worked on selective catalytic reduction, and still there are challenges as well. So here, three technologies are commercially available in this kind of for this selective reduction, like V2O5, like vanadium titanium systems. And then we can say there is a zeolite, which is iron, and then another zeolite is with copper. So there are many times we have to use a combination of these kind of technologies and with the different zeolite materials as well, depending on how what we want to meet or what is the available temperature for the system, and this will give us an idea that how much catalyst to be deposited, what material to be used, and what kind of conversion we are needing. Because again, this is the conversion is depending on what kind of regulation we want to make. So this is how the overall designing we need to develop. Other thing, probably some of you may be knowing that we need to have urea solution available. Like maybe today we are seeing on petrol pump it is not available, but AdBlue or DEF kind of a solution will be available on each and every petrol pump to because the truck and buses, they have to fill this in the tank to work the SCR system. And this is again, these are going to be a big changes in the overall delivery of the fuels on the petrol and petrol stations. These are the basic kind of NVCATs. We say, okay, this is Sutkami trademark, basically NVCAT. So when we say blue is the copper, and yellow is vanadium type material, and then red is iron based material. So we can see that copper systems are really working at a low temperature. Based on the availability of the temperatures, we can give a different kind of catalyst material, and then accordingly the regulations can be met. So overall, just to conclude my talk on that, there are significant efforts has been made to control the vehicular pollution in India, because we know that there is a huge health impact, and this is really a need of the hour, I would say. And yes, India and current regulation worldwide, there are gaps, and I think almost we can say 5 to 10 years gaps, in terms of meeting the regulations. But still, we are very close to the rest of the world. We are, when we say BS6, yes, they are talking about like Euro 6 D or even Euro 7. So there are different regulations. So we need to meet that kind of regulations, or with the EU or with USA. So that will be again, we have to go along to develop these technologies. So there are different technologies are being used, like three-way DOC or DPF, SCR, even LNT, and there are several different technologies to meet the vehicular pollutions. Yes, to meet this one, yes, we need to also look at the washcoat architectures and designing the geometry of the substrates, and what is looking at the engine management and working with the OEMs to how their engines has been developed, and what are the temperatures, and what are the kind of feed gas available for converting the gases. So these all things with working together only, I think this technology can be developed. On the other hand, yes, one OBD2, which is basically again monitoring the systems online in India. I think this is going to be from like in April 2023. Though this is not the fixed date, but so far this is what is being conveyed to almost all OEMs for by Government of India. So once this is coming, then automatically the regulations of bad vehicles will be out, because we have to there will be automatic mill light on your dashboard that can show you, yes, your catalyst is functioning or it is not functioning, so you have to replace the whole system or something. No, I mean, it is not very easy by any mechanic that you can change any time and then change just like old one. So these are the like lot of challenges we have in terms of developing the catalyst and also meeting the air pollution norms by Government of India. So thank you very much for your time and and for your invitation. Yeah.
Thank you, sir, for your informative talk. The session is now open for discussions. So if anyone has any queries, you are requested to ask.
Yeah, I just would like to say something. Hello.
Yes, sir. Yes, sir.
Yeah, I visited your company.
Yeah.
10 years back when Dr. Karsadji was there.
Okay, sir. Yeah, still he is here, sir. Yeah.
Yeah, just say hello to him from me, Rangarao from IIT Madras.
Sure,
That time, they were thinking of introducing Syria zirconia as a component to the catalyst.
Mm-hmm.
What is the ratio? What is the composition of this Syria zirconia that you are introducing in your catalyst?
So there are, depending on, as I showed you, that depending on it can vary, let us say, from 10% to even 50 to 60% as well, because depending on application, it is not a very specific for for a product. It is specific to like I would say one norms to another norms also, and vehicles also. But it can vary from 10 to 50%.
So Syria is 60%.
Yeah. So even 10, sometimes 10%, sometimes 60%. That is a range.
Okay. So is it working satisfactorily?
Yes, sir. Yes, sir. Of course, we are supplying commercially. Yes.
Yeah, I gave a talk on the Syria zirconia in your place. You can recall from Sir Karsadji.
Mm-hmm. Yes, sir. Yes, sir. Sure.
Okay, thank you.
Thank you very much.
Vijay,
Yeah.
I'm Pranjal here.
Yeah, Pranjal.
How are you?
Yeah, fine.
Okay. Vijay, hello.
Yeah, tell me.
As you mentioned that several catalysts, so different temperature, low temperature, high temperature. So is there any types so that we can use that soap in all vehicle, or the types of vehicle we are using the different types of catalyst?
No, it is really depends on vehicle to vehicle and also the designing, because as I showed it you, sometimes we have to within one catalyst we have to coat multiple catalyst. I mean one substrate we have to coat a multiple catalyst to meet such a kind of norms. So there can be zone coating, there can be layering, there can be within zone there are another zones. So because some catalysts they are working at low temperature, some catalysts are working at high temperature. So we have to make a combination of that catalyst and then we have to supply that integrated solution to the OEMs.
Okay. And just one more question, Vijay. Just to know that. So if you mentioned that low temperature means what type of vehicle we are using that catalyst? What type of vehicle? Low temperature, high temperature means what type of vehicle we are using that catalyst?
Low temperature, that is a cold start. Let us say today the cold start challenge is like, as soon as you start your vehicle, that vehicle is at room temperature. So room temperature, that, and you want at your catalyst to function at room temperature. So if it is possible to develop such a catalyst which can work for at room temperature where CO hydrocarbon NOx can be converted, then that would be of course the fantastic discovery, but of course it is not possible. So people have targeted current lower conversion is, let us say, from 150 degrees Celsius. Still that is a big challenge.
Okay. Thank you, Bijoy.
Thank you very much.
Yeah. I'm meeting in after a long time.
Yeah. Okay.
Thank you. Okay.
Thank you, sir. I hope that there are no more questions, and we thank you for joining us once again. Now we shall have a talk by Dr. Ilyas J. Ismagilov from the Boreskov Institute of Catalysis, Russia. He was supposed to deliver the talk earlier today, but due to technical issues, he could not. He has already been introduced, as you all know. I request Dr. Ismagilov to kindly deliver his talk.
Yes, thank you for the kind introduction. Does everyone hear me? Okay. Yes, and could you please let me share the screen? Yes. Okay. Yeah, very well. Moment. Okay. Blah. Second. Yes. All right. Let's see. Just a moment.
Yes, sir, your screen is visible now, sir.
Okay, yes, thank you. Thank you very much. Yes, dear colleagues, many of the aspects which I list, they have been discussed at this very impressive conference. So I would like to say that our work is related in some part to the nanomaterials the issues, and some typical, just to remind, some typical scales which are used. Then in catalysis, of course, quite often the supported types are applied, as can be shown here, and in many cases the special properties are being considered due to geometric or electronic factors. So the issue of the stabilization of nanoparticles of active component on the catalyst support, they have several benefits. That is, we can improve the surface area, the interface formation can be achieved, and also one of the issues if you work with the carbon containing substrates, I mean the raw materials, is decrease formation of carbon deposits. We have used, among the others, some approaches, and the strong metal support interaction, the SMSI, is one of the goals which we go for. And examples of the energetic ratios between the metal and support particles are shown at the bottom. So, for example, in the lower right part, the SMSI situation is shown. Now, in this work, the nickel-based catalysts have been applied to create rather composite lanthanum and other metals substituted systems. You can see typical chemical compositions on the left side, and one of the again, one of the goals which we work with is kind of in many cases, a reversible transformation. That is, you have, for example, you have nickel as shown in yellow as a well dispersed part of the system. Then, upon redox treatments, it can either agglomerate or go back to dispersed state. And these catalyst compositions, they allow to get this approach. At the bottom, the cerium oxide-based types of structures are shown. So, for the synthesis of materials, several parameters have been varied. You can see on the screen. Our group has developed the approach after several years of experiments based on a polymerizable complex method. And basically, here you see the variables which are possible to control under using this approach. The stoichiometries are shown here. The metallic dopants are lanthanum and magnesium. The physical-chemical properties have been characterized, as well as the functional properties. In our case, the steam carbon dioxide, methane reforming, and also the autothermal ethanol. That is, methane is organic, CH organic, and ethanol is the oxygenate. Carbon dioxide reforming often is called dry methane reform, DRM. So here are the compositions which have been synthesized. So you can see that the majority is represented by cerium or lanthanum modified or magnesium modified ceria, and oxidic nickel part. The picture with some structural steps for you. You can see that in fact the organic assisting compounds have been used. So to make eventually the required nanoparticle size, location, electronic state. So finally, you can see that from the at the bottom of the picture, from the polymer gel, eventually a solid-like solution is obtained, shown here, and the sequence chemistry-wise also represented. So eventually, it's been finished by the oxidative and reducing treatments at 500 and 800 degrees Celsius. So an illustration of the thermal analysis of the gel precursor. Basically, there is a number of details, quite understandable, but the main conclusion is that in fact, the thermal genesis is weakly dependent on the molar ratio, one of the parameters of lanthanum to cerium or magnesium cations. So now eventually, the chemical composition which was obtained, you can see that by stoichiometry, if we recalculate from weight percent to molar percent, these are quite representable. For example, if you see regarding the nickel content, it's around 9 point something 10%. So the main conclusion that yes, indeed, the XRF, X-ray fluorescence analysis has been done, and composition corresponds to calculated value. So then a number of physical-chemical characterizations have been applied. I will go quickly because time is precious. They're listed here. So the textural properties using the low temperature nitrogen absorption, X-ray analysis has been done, electron microscopy, Raman, energy dispersive analysis, also the TPR by hydrogen, and thermal analysis as an example you have seen on previous slide. So briefly, you can see just to get an idea. Here is a combination that indeed, depending on the sample composition, you get different. These are the scanning electron micrographs. You can see different, in many cases, different morphologies, and the textural property in general. If you combine the information from the slide, that there are some specific types of the adsorption isotherms. If we decrease the X, the substitution degree, then the specific surface area increases. Typical values for the pore volumes and pore diameters are shown, and also there is a dependence of specific area on the sample brutto qualitative sample composition. That is, lowest is when magnesium is used, medium when lanthanum, and highest when nickel. So structural properties, in this case, the XRD factor has been applied. The models using different substituting cations, cerium 4+, lanthanum 3+, and magnesium 2+, have been used, and lattice parameters are shown here. You can see somewhat lower than 1 angstrom and somewhat higher with lanthanum. Relative positions of the cations and anions, oxygen anions, are shown on the picture. So also some analysis of such parameter as a unit cell volume has been done. You can see there is a correlation. Now, the transmission electron microscope has also been used, and there is you can see, in fact, in this case, the lattice spacing is different if you compare with between the three types of samples. Not substituted lanthanum and magnesium substituted. You can see also different phases. For example, the only situation where heterophase oxide phase is formed is when magnesium is used. With lanthanum substitution, no lanthanum oxide is seen. There are some correspondences with the Raman spectra. Raman spectra being used at the moment. They are being discussed and prepared for publication. Also, there is, just to illustrate, that there is an effect of calcination temperature. Just a correlation between the XRD graphs and bar diagrams. Eventually, what was important that one important factor which has been used is temperature. So since the process, especially the steam carbon dioxide reforming can be realized at rather high temperatures, so up to 900 degrees Celsius, samples have been calcined, and so in fact, the corresponding analysis have been done. So the main one of the main conclusions, we have actually seen that in our previous works, that the lanthanum nickel type of perovskite is observed. So just some correspondence between the TM and EDX. You can see that pretty much there is a rather localized and uniform distribution based on specific X-ray emission lines of nickel, cerium, and lanthanum and magnesium. So now, just in this case, this is one of the works we have just started, but there have been some particular reasons. So we have just recently resumed measurements in situ, XRD measurements in the reducing medium, that is hydrogen-containing mixture, and you can see for now what we have obtained. There are some variations of the unit cell volume and also the coherence scattering region of, for example, based on the cerium dioxide lattice type, depending on temperature. Also, in fact, a correlation has been done between the XRD and temperature programmed reduction. I should better concentrate on this picture on the right. So basically, what happens is that in the temperature range, several transformations are observed. Some mixed cerium nickel oxide surface structures, then nickel forms somewhat over the individual oxide or solid solution, and then in other cases, when, for example, when the magnesium oxide is used, excuse me. Sorry about that. Yes, so the nickel MgO and eventually some reduction of cerium. So there's similar, more precise analysis using the transmission electron microscopy scanning and the EDX has been done. You can see there's quite a reasonable correspondence between the pictures. Actually, the stoichiometries of the reactions are shown here. So conditions and stoichiometries. The steam carbon dioxide reforming of methane and the ATR using the stoichiometric amounts of oxygen and steam. Let me briefly remind. Well, more or less, the carbon dioxide reforming reaction has been known for about 20 or so years, but the idea of outer thermal reforming is that, in fact, there are two types of reactions combined here. The moderately exothermic partial oxidation using oxygen and endothermic steam reforming. So in this case, the stoichiometric quantity of partial oxidation provides additional thermal energy to drive the concurrent steam reforming. So, and you see in both cases, of course, hydrogen is one of the gold products, both carbon monoxide and hydrogen. So, just to go here, you can see that that is one of the most impressive results. Indeed, modification of cerium by lanthanum. This is the ethanol after ATR. It does make a more stable catalyst. Reaction time is about 1 to 24 hours. You can see modified catalyst is more stable. Also, it has less content of carbon deposited on it, and also some other parameters regarding the yields of products have been carefully measured. So and now this is the steam carbon monoxide. You can see that the values of better take a look at the yields of gold products. It's possible to obtain between 60 and almost above 90% of hydrogen yield, and so this is considered the magnesium modified cerium nickel oxide is considered as for now among these series as an optimal material which is highly resistant to carbon deposits and provides a high yield of target reaction products. So let me finish. So in this work, the genesis and physical, chemical, and functional properties of these materials have been determined, and the correlations have been shown that if lanthanum is used as a modifier, nickel cations are stabilized in the composition of solid solution, and magnesium in the composition of a direct magnesium nickel oxide. High temperature treatment can be used, and materials exhibit rather quick resistance to carbonization. So, and eventually, I would like to thank a number of colleagues from the institute, and I would like to say that part of this work has been started during the joint Department of Science and Technology, India, and Russian Foundation for Basic Research joint project with a group of Professor Pankaj Bharali from Tezpur University of Science and Technology. Thank you.
Thank you, sir. Now the session is open for discussion.
Let's see.
Are there any questions?
Where am I?
Okay, I guess there are no questions. So thank you, sir, once again for joining us.
Thank you as well, ma'am.
With this, we come to an end to the technical session 3. And without further delay, we shall be starting the technical session 4. To begin the technical session 4, we are honored to have amongst us Professor Matthias Beller. Professor Beller is the scientific director of the Leibniz Institute of Catalysis, Rostock, Germany. The work of his group has published more than 1,200 original publications, reviews, and more than 90 patent applications have been filed by them in the last decade. He has received several awards, including the Otto Roland Medal, the Leibniz Prize of the DFG, the Gay-Lussac Alexander von Humboldt Prize, the Emil Fischer Medal, and so on. He is also the Vice President of the Leibniz Society, one of the major science organizations in Germany, and a member of the German National Academy of Science, Leopoldina, and 3 other science academies. He is associated with various prestigious journals and is an editor of the Journal of Catalysis. His work focuses on important aspects of homogeneous catalysis, especially of transition metal catalysts. Sir, I'd like to request you to kindly deliver your talk.
Yeah, thank you very much for this very kind introduction. Can you please turn down the microphone? I hope it's better now, yes. I think if everybody turns down the microphone. Yeah, this should be now better. Okay. First of all, I would like to thank you for your kind invitation. It's really a pleasure participating. So I joined the conference around 2 hours ago. So here in Germany, it's still early morning, or it's morning. We have now 9:40. So you started quite early. So it's really a pleasure participating. And I would like to tell you a little bit about our recent work on innovative materials for specifically non-noble metal catalyzed transformations. So I hope you can see my screen.
It is visible, sir.
Okay, great. So before starting, I should thank the people who really have done the work. I have the pleasure to have to cooperate with a number of very talented young students and postdoctoral fellows. As you might guess, this picture was taken before the COVID crisis. So now we are not allowed to take pictures like that. So this is already 1.5 year old. But you will see on some of the slides, especially the ones which show the more recent results, you will see the people who have done really the work. So, but it should be clear, the credit you mentioned in the introduction really goes to these students and postdoctoral fellows, because they really did the work. In my group, we are interested in, I would say, more or less 4 areas. We have, based on my background, I'm a synthetic organic chemist. We do a lot of still organometallic chemistry. So 1/4 of my group is still doing classical organometallic chemistry. Because this is not the topic of our conference today, I will not talk about that thing. In addition, we are still interested in synthetic methodologies at the moment, specifically also making fluorinated molecules and things like that. But again, because this is not the topic of the conference, I will also not touch this type of area. The topic I will talk about is synthesis of new materials. And this is an area we entered around 15 years ago, because at that time, our research institute, we are a research institute which is associated with the University of Rostock, but is independent from the university. So we belong to one of the German science organizations, as you pointed out in the introduction. So around 15 years ago, we merged our institute, which was specialized in homogeneous catalysis, with an institute specialized in heterogeneous catalysis. And now we have all the characterization tools, and we have scientists in one place working on materials, heterogeneous catalysis, but also synthesis and homogeneous catalysis. And at that time, we thought it might be interesting to bridge these areas, or to go into that direction, because we have now the characterization tools available and the expertise and so on. And as you will see, inspired by homogeneous catalysis, organometallic chemistry, we moved into that area. And I will more talk about these materials which you see here on the slide in one of the next slides. So we started making materials based on an industrial cooperation project some years ago. At that time, we developed very efficient molecular defined non-noble metal catalysts for carbon dioxide hydrogenation and for formic acid dehydrogenation. And this is of interest in the area of hydrogen storage. But again, I will touch this area because of time. I will not touch it. So when we discussed possibilities for applying such reactions in industry, the people we talked in industry always told us, yeah, it's nice to have such a homogeneous catalyst, but in industry, we would really like to apply a heterogeneous system. And because of that, we started, I would say, very naively on immobilization of non-noble metal complexes on various supports. So what we did at that time is we used defined and in situ generated iron, cobalt, nickel, but also ruthenium-based phosphine and amine complexes. We prepared them like it's typically done in homogeneous catalysis. And then we simply added some supports like carbon, titania, alumina, silica, and so on. And so after this physical absorption of the metal complex on the surface, we dried the materials at low temperature, I have to say, and then we looked for catalytic activity. And we studied various reactions. We looked for nitro reduction, which is one of the most simple, I would say, hydrogenation reactions, but we also looked for carbon dioxide hydrogenation and formic acid dehydrogenation reactions. Unfortunately, all the materials which we tested, they were basically all the materials which we tested, they were basically not active. And then, like often in science, serendipity came into the game, and we were lucky because the postdoc, Dr. Jagadesh Rajanahali, who is now group leader in our institute also, he was working together and in cooperation with a German electrochemist, Annette Sokos, and she prepared at that time non-noble metal catalysts, or she prepared materials, non-noble metal-based materials for electrodes. And all of her materials, most of them at least, were prepared by pyrolysis and high-temperature heating processes. And because none of the supported low-temperature materials was active, Jagadesh provided some of the materials to Annette, and these, let's say, nicely organometallic complexes on the surface of the support, they were pyrolyzed, typically in between 600 and 800 degrees. And to our surprise, the materials were active. And I show you one of the first examples of this activity is, so this was a system where we had iron phenanthroline complexes, so relatively simple iron salts. We use a nitrogen ligand, a coordinating bidentate nitrogen ligand phenanthroline. We mix everything. We add carbon to that complex. We immobilize it, and then we pyrolyze the system. And to our surprise, the homogeneous catalyst is not active. The non-pyrolyzed catalyst is not active, but the pyrolyzed materials shows very good activity for nitro reduction. And in fact, it's acting with respect to selectivity much more like a homogeneous system than classical heterogeneous one. So it was very selective. So we could hydrogenate nitro compounds in the presence of labile carbon boron compounds. We could hydrogenate nitro compounds in the presence of alkynes. I have 1,2 dicarbonyl compounds, which are typically reactive. A number of heterocycles are well tolerated. And as you can see, the efficiency of the process was very well. So in fact, we have most of these type of reactions are known with noble metal complexes. In fact, we have a relatively simple non-noble metal iron-based system, you can say, which behaves like a noble metal complex. How is this possible? I will come to this in a minute. But before I talk about the mechanism, about the activation, and why materials are special, I just want to briefly elucidate what we have done since then. So what can one do in this area? So, of course, we can vary the support, we can vary the metal complexes, we can use different ligands, bio-based ligands, as I will show you some examples of bio-based waste, and we can look for new reactions. And in fact, we have done this since that time, and I will give you only, because again of the time, some brief examples, and I will also show some unpublished work. First of all, let me talk about the ligand, because if you simply pyrolyze a metal salt without the appropriate ligand, the material will be not active. So the organic ligand which we use in these processes is quite important. So you can use amines like phenanthroline, I pointed this already out, but you can use very simple, cheap compounds. This, for example, Dr. Basudev Saho, he used chitosan. Chitosan, as you might know, can be easily derived from chitin. I will give you an example also from chitin in a minute. And you simply mix this bio-waste. Chitin is a large-scale bulk bio-waste, which, for example, originates from shrimp shells. And you can simply mix this bio-waste with, again, simple cobalt salts or nickel or iron salts. You mix these things in aqueous alcohol. you provide the corresponding complexes, you dry, you get the material, can be nicely handled, but again, it's not active. But once you pyrolyze it, this material, it becomes active. Depending on the ligand, I should also point this out, we can vary the metal content. In this case, for example, we can achieve metal contents up to 10% in the catalyst. If we use bidentate, amines like bipyridine, phenytoline, and so on, we typically have metal contents between, I would say, 0.5 to 3% metal content. This is some more recent work here. Chitin behaves different from chitosan. And what you see here, this is a matrix of, let's say, one catalyst system, cobalt based as a metal, chitin as the ligand, and then we have various additional supports in this reaction. And you can see here the pyrolysis temperature, you see the color code, this is hydrogenation of a nitrile. This is more difficult than nitro reduction, but still it's an activated, I would say, functional group. Somewhat, let's say, similar reactivity to carbon dioxide for hydrogenation. And as you can see, the various materials, despite it's the same metal, it's the same pyrolysis, it's the same, let's say, procedure, they behave quite different. The most general material is the material where we add magnesium oxide to these systems, or where we support the organometallic complexes on magnesium oxide, and then we get in basically over a wide range of pyrolysis temperatures, we get very good yields. And this material, I will tell you about the structure in a minute. This material, we believe, is one of the most general nitrile hydrogenation catalysts known to date. This was published in the 1000th issue of Chemistry, an invitation issue. So Chemistry European Journal last year published the 1000th issue of the journal. And we believe that, or we compared this catalyst with, let's say, commercially available benchmark catalyst for nitrile hydrogenation, but we also used some in-house catalysts, and we compared with respect to functional group tolerance, and we looked also for some difficult substrates like pyridinic nitriles, and we believe this is really the most general nitrile hydrogenation catalyst which we had, at least in our hands, under these conditions. So far I only showed you reactivity, but I didn't said anything about the structure and the mechanism, why these materials are so specific and active. So what we in general observe structure-wise is we have in this pyrolysis processes we perform, or we produce metal nanoparticles, and these metal nanoparticles are typically core shell type particles with a metallic core and some oxidic shell. But the really interesting thing is, in the surrounding of these core shell particles, we see carbon phases. And we see different kinds of carbon phases depending on the pyrolysis temperature, depending on the ligands, and so on. Sometimes, like it's illustrated here, so this is simply a picture, it's of course not reality, but sometimes it looks like, we call it carbon flakes. Sometimes you have graphene type layers, so small layers. Sometimes you have more graphitic type, larger carbon phases actually surrounding the metal nanoparticles. Depending on your ligand which you are using, these carbon phase is doped, for example, with nitrogen, so you have additional nitrogen, or if you have other, let's say, donor atoms, there might be additional donor atoms. And I'm just going back for 1 second here. If you see these materials here, for example, then we generate a material. We have a magnesium oxide support. On this magnesium oxide support, we have metal nanoparticles, and then we have the metal nanoparticles surrounded. Actually, here you see, I hope you can see this, the red, let's say, coverage a small layer of carbon basically surrounding that. So some more schematic view on this type of structure. So in general, we believe we have the metal nanoparticles on the surface. For example, if we have a carbon surface or an n-doped carbon surface, this is symbolization of the n-doped carbon surface. In the close surrounding of the nanoparticles, which, depending again on the conditions, have sizes between 5 to 10 nanometers, but sometimes also 50 to 100 nanometers, we have, for example, nitrogen-rich areas. And for a number of the specifically dehydrogenation and hydrogenation activity, these nitrogen doping is extremely important, because without nitrogen doping, you don't see any activity. And we believe the actual action is very similar to some molecular chemistry. And this is an ion complex. In fact, this is the ion complex we synthesized first, a molecular defined species. This is an ion complex which is able to activate hydrogen at 1 bar at room temperature. So you have a single ion metal center. This was the first example for an ion species where this was possible. We have a single ion species center, which is able, under such mild conditions, to activate hydrogen. And crucial to that is the let's say, cooperation, the cooperativity between the nitrogen and the ion center. And that's so you have some sort of heterolytic cleavage, providing an ion hydride and some sort, let's say, of nitrogen-hydrogen bond, where hydrogen has the character of a proton. And we believe exactly the same happens in these type of reactions. And we have, of course, no molecular proof for this, but we have many indications, and I want to show you just one. This is my only slide with respect to homogeneous catalysis. This is our ion catalyst, as I said, which we developed for a molecular defined catalyst for nitrile hydrogenation. And if you look carefully at the conditions here, alcohol, 30 bar hydrogen, 100 degrees, and you compare it to the catalysis with the nanoparticles, it's very similar conditions. In fact, some of the nanoparticles are more active than this homogeneous molecular defined system. So, of course, we have very nice, let's say, catalytic behavior, but it's very difficult to predict let's say, the structure of the materials and the reactivity. So it's lots of, let's say, trials and error. And this, of course, this is something we don't like in science. So I sometimes call this pyrolysis, it's some sort of exploding Lego approach. You get lots of things, but you are not sure what exactly, let's say, defined structure you get on the surface. And in order to develop such catalysts in a more defined way, we developed pyrolysis, not of organometallic complexes in recent years on the surfaces of supports, but instead what we are doing is we are putting molecular organic frameworks, so metals, non-noble metals in very specific, let's say, position of the metal organic framework. We put them on a support, for example, carbon, or we use coordination polymers. And because you can very precisely control the structure of the metal in such a supported MOF or in such a coordination polymer, depending on the linkers you are using, you can vary the size and control to some extent the size of the particles. And if the spacers are very long, so the individual metal atoms are relatively far away from each other, then you are able to produce what we, let's say, single metal centers on the surface. And these single metal centers, as you might know, in heterogeneous catalysis, it's a very active and interesting area. They behave very nicely. And Kati Varan, a PhD student working together with Yagadesh, he used this type of catalyst for reductive amination chemistry, because amines, as you might also know, play a prominent role in pharmaceuticals and agrochemicals, and the typical way in industry to produce such amines is reductive amination chemistry, and he showed that these type of catalysts are very general catalysts for this type of reaction, tolerating a wide range of conditions. So at the very end, I would show you some unpublished work, and I will show you also that you can do, let's say, new type of reactions. I will now, at least to my knowledge, show you a completely new reaction also, which is possible with these nanoparticles at the end. And the reaction I'm talking about, you might think it's not interesting at all, or it's only interesting of small scale. It's labeling technology. But labeling technology, any drug which comes onto the market nowadays needs, let's say, some labeled compounds in order to understand the behavior in biology and so on. So this is for a long time, labeling or labeled analogs of bioactive compounds is, I would say, a very important part of the pharmaceutical development. And so many methods exist: classic acid-base, heterogeneous, but also homogeneous. There is more recent developments. But there is one interesting thing which you might not know. In recent years, there is also not only an interest in performing such reaction on small scales, but also on some larger scale. Because at the moment, there are several drugs in clinical phases which, instead of a carbon-hydrogen, have carbon-deuterium bonds in the molecule structure. The reason for that is that if you put deuterium instead of a hydrogen at a crucial position in the drug, then the biodegradation, for example, is lower. So the efficiency of the drug is higher. And one drug is already at the market, it's Austedo, but several other examples are on the market. And for such compounds, you need also practical methodologies. But most of the developments in the past, they are very, I would say, make use of very specific or sophisticated systems because you only do it on very small scale. So following the concept I've shown you before, Dr. Wu Li, a very talented postdoc from China, now in China back, he prepared materials by combining, I would say, two of the most ubiquitous materials on Earth. So we use iron salts. Iron is the most abundant metal on Earth. And he used as a ligand the most abundant biopolymer on Earth, cellulose. So you can mix this. This is undergraduate chemistry. Basically, any high school student can do that. So you mix iron salts with cellulose. You take away the solvent, aqueous ethanol, and then you pyrolyze this material. And then you get what we call iron cellulose. I will show you the structure in a minute. And if you look for deuteration reactions, and you look, for example, established noble metal systems, then we use this material as a model system because we were interested in deuteration of sp2 carbon hydrogen bonds, and we didn't want sp3 carbon hydrogen bond deuteration. Then we found that the iron cellulose system is outperforming all other materials which we tested until that time. Now we have some even better ones, but at the beginning of or in the middle of the last year, these were the best systems we had in hand. The interesting thing is, and now this is a new reaction, as I said, the interesting thing is deuteration occurs in D2O. D2O is the cheapest source of deuterium. So D2, deuterium gas, is much more expensive than D2O. And so we use this iron catalyst with D2O, interestingly, in the presence of hydrogen to activate the catalyst, and we observe deuteration. And here you see some examples. You see drug-like structures. You see, for most cases, you see the generality of the method, and you see, let's say, also the efficiency of the labeling procedure. what is the specific thing again of this catalyst? So the specific thing of this catalyst, it's also the catalyst, what we know from EPR studies is doing some, let's say, radical type water splitting. And the catalyst is doing that or is relatively stable because it has a large cover of carbon surrounding that. So compared to the catalyst I've shown you before, we have relatively large phase here of carbon surrounding the iron nanoparticles. And this also makes the system comparably, let's say, stable. In general, we see, let's say, iron metal, iron carbide phases, and these phases are stabilized by a shell of up to 13 graphene layers with a thickness of 6 to 10 nanometers. So the catalyst, as I said, it can be very easily prepared. And so you can perform these reactions on relatively large scale, at least from an academic point of view. So here you see experiments on 300 gram scale. So we have now some deuterated compounds in kilogram scale. So if you're interested in some deuterated compounds, we're still looking for application of these type of things. And as you can see, also the recycling is quite special. What is important for labeling for any practical application, especially when you use heterogeneous catalysts, you have quality of deuteration. So when you use it, you must know the next time it works the same. And as you can see, the quality of deuteration, the reproducibility is really high, and we believe it fits or is possible also for an industrial application. So this actually I wanted to tell you. Stay healthy, don't get infected. Thank you very much again for this kind invitation. I'm happy to answer any questions.
Thank you so much, Professor Beller. I am Pankaj Bharali, so coordinating this particular
Nice to see you.
Conference. Thank you so much for your very illuminating lecture. And I ask the participants, if you have any query, kindly unmute yourself and then you can have the query cleared with one of the eminent professor in the field of catalysis. Thank you so much, sir.
Can I ask a question here?
Yes, sure. Professor Jayanta.
Yeah. So,
Sure.
very nice talk, Professor Bella. This is Jayanta from ISA Bhopal. I have a query. I mean, in the last section of your talk, the deuteration, the most exciting one, the deuteration reaction. Yeah. So I guess it is activating the dihydrogen first, having the iron hydride now, and that is getting exchanged with your D2O?
Yeah, thank you very much for this question. Thank you also for your kind words. So the deuteration works also without the hydrogen. Okay. But the yields are generally 20% less, and we cannot recycle the catalyst, so efficiency. So, okay. So what we believe we have done operando XPS spectroscopy in the presence of hydrogen. Okay. And what we see that the iron zero species, so despite we have the carbon layer, when we put hydrogen onto the system, yes, iron oxide, we have more iron metal, and we believe this iron metal is very important. Right. Of course, during the reaction, let's say iron, as we all know, is oxidized easily. Yeah, and even in water, this happens. And interestingly, also, I would have not guessed this is pure, let's say, experimental finding. I would not have predicted that. Right. The hydrogen is not activated by the iron and then provided the hydride, but it's really the reaction of the D2O with the iron. D2O with the iron. Wow. Yeah. Wow. Okay. In one of the examples in that slide,
I found that the NH, I think indole NH probably, that remains as NH. So does it not get exchanged with the D2O-D?
No.
I found that NH is remaining. Yeah.
Yes, you're absolutely right. Of course, after the reaction, there is, of course, D there. But what we typically do, I have not mentioned that, what we typically do is, after the reaction, we do aqueous workup.
Okay, then it's fine. Yeah, then it's fine.
The CD is not exchanged, but ND and OD, of course, are exchanged.
Yeah, of course. Yeah. That is, of course. Yeah. Thank you very much for your insights. I was wondering, I was very much curious about the reaction mechanism, whether it is H2 or D2O, where it is getting the D exchange. Yeah, thank you. Thank you.
It's D2. D2O.
D2O, yeah. Good. Thank you.
Any more questions? So I guess that's all. Thank you so much, sir, once again for your very informative and equally interesting talk. Proceeding forward.
Thank you very much again.
Thank you, sir. Proceeding forward, we have a talk by Dr. Sanjay Kumar Singh. Dr. Singh is an associate professor at IIT Indore. He was a JSPS fellow as well as Humboldt fellow before joining the current position. He has gained extensive expertise in the area of hydrogen production and storage, and currently his research focuses on the design and development of new and efficient catalysts and materials for hydrogen production and storage, carbon capture, utilization, and biomass transformation to fuels. He is an International Advisory Board member, CAM, and a winner of Award of Excellence in Teaching, IIT Indore. He has numerous publications in reputed journals, more than 5 patents, and 2 book chapters to his name. I would like to request Dr. Singh to kindly deliver his lecture.
Thank you very much. Please allow me to share. So my slides are visible?
Yes, sir, your slides are visible now.
And is it in the full? Excuse me?
Yes, sir.
So my screens are you able to see?
Yes, sir, your screen is visible now. We can see the slides.
Okay, good. Okay. So thank you very much. Thank you for the kind introduction. And first of all, I would like to thank the organizers, particularly my friend, Dr. Bharali, and for inviting me and giving me this opportunity to share my work at this platform. So since last day, we have been listening to several talks, and many of these talks are also centered on hydrogen production, CO2 utilization. Recently, this morning also, Dr. Jayanta discussed about how to utilize CO2 to convert it into liquid hydrogen storage materials. So in that line, I will be discussing in today's talk. And my talk is mostly on how to utilize these liquid hydrogen storage materials as a potential hydrogen source. So let me start with a little bit of background. And so Jayanta discussed about this talk and this particular rising of CO2. And I'll see, I born somewhere in 1979, and since then you can see like CO2 emission is increasing, and it is still increasing. And since childhood we have been listening to these two words like global warming and greenhouse gases, and this still increasing CO2 emission indicates like we are not serious about these goals. So now we have reached to a level that there is no way back to just to find some sustainable solution so that we can control CO2 emission, because now the situation is kind of like as our survival is dependent on all these things. So what we can do, like we have to really find out a solution so that we can cater our energy demand, and this demand, really there is no such energy crisis as of now, but what we need, that we need a sustainable solution to cater our energy, and in that manner we all are working together. Okay. So if you see, mostly we are talking about CO2 emission, and the major contributor here is the transport sector. And transport sector, if you see, like it is still increasing and increasing day by day, because most of these vehicles are running on fossil fuel. Of course, recently we have seen electric vehicles are coming up, even in my city, and of course in most of the cities of India, the public transport is running on electric vehicles, battery based vehicles. So, but what we have to think, in this particular slide, you can see the carbon footprint. This is important because we have to see, like, whatever things we are using, what is the ultimately, whether it is suitable for the environment or not, how much is the carbon emission is there. So if you think in that way, particularly the electric vehicles, if you see, there are two things, two different types of electric vehicles are discussed here, and one has zero carbon emission, and another one is having a second largest carbon emission. So how to compare these two things? Like when we have more electric vehicles, and we need more electricity also. And unfortunately, in India, if you see, or even in the global scenario, most of the electricity are being generated from fossil fuels. Still coal dependent electricity generators are there. So in one way, we are using electric vehicles, thinking like it is a very much sustainable system, and it is for the benefit of environment, but we are generating more and more electricity to charge our electric vehicles used by burning fossil fuels. So what we need, like we need an ultimate solution to cater all our energy demand, and in that manner, if you see, like hydrogen is at the centerpiece. So hydrogen, considering hydrogen just as a fuel for of vehicles, it will be a kind of injustice to it. So hydrogen has to be used in all the areas where we need energy, like electricity generation and all those things. So of course, hydrogen is a clean fuel, and because it provides CO2 free transport, and it will certainly reduce our dependency on fossil fuel that is very much required. And of course, there is no greenhouse gas emission, particularly like because when it will be utilized in fuel cell, it will be generating only water, and of course there will be no air pollution. This is a very good thing about hydrogen, and it has also a very high energy content compared to fossil fuel. And if all these technologies of hydrogen and fuel cell technology were achieved, so we can be able to reduce the greenhouse gases significantly. So this is ultimate solution when we have to use hydrogen in a holistic way, and not just as a fuel for vehicles. Because in one way you can think about, if electricity is also generated from hydrogen, so the electric vehicles and hydrogen based technology become complementary to each other, and they can grow all together. So in principle, the hydrogen-based society has three components: hydrogen production, hydrogen storage, and hydrogen utilization. Of course, in all these sectors, there are challenges, and because most of the hydrogen production happening these days, of course, there are very recent new technologies have been evolved, but still most of these dependent on the reforming Professor Elias discussed about reforming of ethanol and methanol. So reforming is one of the process which is being used, but again, in all these reforming processes, they work at very high temperature, and it also generates CO and CO2. So that again, we have to find a proper solution for hydrogen production, and the second thing is the hydrogen storage, which is indeed a bottleneck to materialize this hydrogen-based society, and particularly the conventional technology is the storage of hydrogen in high pressure tanks, and the other way is to solid state materials. And of course, liquid hydrogen storage materials are also coming up in a very good manner. So that is also the few of the things that needs to be combined all together in hydrogen storage system. Utilization component, of course, as I mentioned, like electricity generation and all these depends on the how to utilize this hydrogen, particularly through fuel cells. So fuel cell technologies needs to be developed. So altogether, if all these sections like production, storage, and utilization work in a synchronic manner, then we can be able to materialize this hydrogen-based society. Let me talk about something from the Indian perspective. What is government of India has recently mentioned about the hydrogen national hydrogen mission, and we have seen recently few of the development in this sector also, like in one of the Union Territory of India, the bus developed by Tata on hydrogen fuel, and recently a battery-based electric vehicle has been converted into a fuel cell-based vehicle, and the heritage train is there is some still we can see some of the development in converting the heritage train completely into the fuel cell based. So there is significant progress, and not only at the researchers level, because hydrogen development and those things have been reported very long back, but at the government level also, and at the industry level also, the people are now understanding and the importance of hydrogen. So that's why there is so much of progress we can visualize. Now, what are the challenges associated with hydrogen? And if you see, like, one of the major challenges is safe and efficient storage of hydrogen for onboard application, particularly the small vehicles. So imagine like 11,000 liter tank will be required to run a hydrogen fuel vehicle for 100 kilometers if we don't use it high pressure. So that is one of the major challenge. And when we talk about pressure, such a high pressure, then of course the safety is one of the major concern. And there was an incident long back, and so that thing needs to be changed, and it is changing, of course. And once everything is go in a very good manner, then and we are able to see so many development on hydrogen based vehicles, so then there will be a requirement of large amount of hydrogen also. So we need to have a cost effective and large scale production units also, and not just like burning coals to produce hydrogen and again releasing CO2. So the similar way I mentioned about electric vehicles, this is also one of the key component where how we are producing hydrogen. I'll come to this in a moment. So what are the different ways of producing hydrogen? So industrially, as I mentioned, like there are several ways: reforming, water gas shift reactions, cracking of methane, ammonia cracking. Those things are still there. Electrolysis of water is, of course, is a zero carbon emission system, and that, but still it has some of the challenges associated with its the commercial to utilize it properly in the commercial level. So as I mentioned, like still 95% of hydrogen produced globally is from hydrocarbon. So when you think about if we generate hydrogen from hydrocarbons, so there will be so much of carbon dioxide emission again, and it is in way we are not able to attain the sustainability kind of that target we are not able to achieve if we are producing large number of carbon dioxide with per unit generation of hydrogen gas. So we have to have a sustainable system, not only in the utilization of hydrogen, but also for the production of hydrogen. You can see still very less amount of hydrogen is being generated from electrolysis of water. So based on the way hydrogen is being produced, there are different type of hydrogen gases, like brown hydrogen, which I mentioned, like produced from coal, and there so much of CO2 is generated, so it is released in the atmosphere. So it is not acceptable. The gray hydrogen, utilizing methane, natural gas, and whatever CO2 is being released, it is also released into the atmosphere. But when we use it in a systematic manner, that if we can have a system to capture the released CO2 and it has been properly utilized or maybe recycled back to methane or methanol and those kind of things. So then this kind of hydrogen produced from natural gas, but it is considered as blue hydrogen. The ultimate thing is to have a system, green hydrogen, where it is produced from renewable sources. There is no ultimate CO2 emission. So basically the brown and gray hydrogen have high hydrogen carbon content, whereas the blue hydrogen has low carbon content, while green hydrogen has zero carbon content. So let me take you to this particular slide where several kind of hydrogen storage materials are compared along with the liquid hydrogen storage material, and you can see, like in these dotted line, the DOE target, where one need to achieve not only the gravimetric capacity, high gravimetric capacity, we also need to achieve high volumetric capacity. So in that manner, you can see at least few of these liquid hydrogen storage materials are listed here, like methanol, hydrazine, and ethylene glycol. And these are having very high hydrogen content, and they can be promising, can be utilized as a promising hydrogen storage material. So these liquid hydrogen storage materials, or liquid organic hydrogen carriers, LOHCs, are very simple molecules, and they can easily dehydrogenate to convert into, like here, a simple alcohol converted into aldehyde, and then again it is recharged, or basically, if I talk in other terms, it's dehydrogenated to come back to its original position. So this charging and discharging process can be a reversible process and can be achieved with the intervention of a suitable catalyst. So advantage with using this liquid organic hydrogen carrier is that they are liquid, so there is no issues with its transportation and storage, and also at the same time the dispensing is also not an issue using the current infrastructure of petroleum which is used there. And it can generate hydrogen on demand. So everything, if work together, then it will be a great thing to have an onboard hydrogen storage system. So there are so many hydrogen storage materials or liquid hydrogen storage organic carriers are developed so far and discussed also in a few of the talks in this presentation, in this conference. So we are also working on all these systems. But in today's talk, I'll be discussing mostly on methanol. I'll take one example from methanol, and if time permits, I'll also discuss about formaldehyde. So methanol, as you have seen in that chart where I have compared different type of hydrogen storage material, so methanol has a very high hydrogen content of 12.58%, and it also has a very high volumetric content of 99 grams per liter of hydrogen. So if it is converted completely into hydrogen, if you see simply, like it has 4 hydrogen atoms and carbon and oxygen, so basically in the presence of 1 molecule of water, it can generate 3 moles of hydrogen per mole of methanol. So, of course, and it can be converted, reproduced from carbon dioxide. Dr. Jayanta has discussed about it this morning. So this, and it can also be generated from biomass waste also. So it is quite a good candidate for hydrogen storage application. And you can see, like, industrially, methanol reforming at above 200 degree Celsius, it can be converted into CO2 and hydrogen molecule. But again, these processes where you have CO2 and, like for fuel cell application, the hydrogen purity is one of the crucial thing. And again, in terms of industrial and economics, if we talk about, so scrubbing and the purification of this mixture of gas is again it will cost something. So in that respect, you can see, like, from methanol to hydrogen and CO2, the complete hydrogenation, complete dehydrogenation, it follows three processes: methanol to formaldehyde, and further very quick transformation of formaldehyde to formic acid with the release of hydrogen molecule, and then of course formic acid into carbon dioxide and hydrogen. So if you see, like, from methanol to formic acid, there are 2 molecules of hydrogen is being produced with the addition of 1 water molecule, and there is no CO2 production. So if you can restrict this reaction from methanol to formic acid with the release of 2 hydrogen molecules, then there will be no CO2 generation, and we will be having formic acid, which is again a very good hydrogen storage material, and it has also commercial value for different applications. Literature discussed so many homogeneous base complexes. Professor Baller also worked on this, and they have developed a series of complexes, very active molecules from manganese or iron or iridium or ruthenium based PNP type of homogeneous complexes for hydrogen production from methanol. I've just mentioned here, like, one of the example where they've used ruthenium PNP hydrido complex at 90 degree and hydrogen methanol. So this productivity is one of the issue with most of these catalysts. The conversion is not complete as such. And again, using one of the platinum based on supported on molybdenum carbide at 190 degree, the hydrogen is being produced from methanol at low temperature. And a platinum supported on cerium oxide is also reported, but of course it is at 300 degree Celsius, and you can see the produced gas has CO also. So again, it is an issue. But of course, what you can see here, the particle size has a significant role on the efficacy of these catalysts. So with all these results, we have developed ruthenium supported on carbon catalyst as for the hydrogen production from methanol. It is purified hydrogen, and there is no CO2 emission because it restricts the reaction up to formic acid. And we have used ruthenium benzene dimer dichloro-based as an organometallic precursor to generate ruthenium nanoparticle in situ. And you can see, like, it can generate hydrogen gas with an efficacy of hydrogen 0.45 moles of hydrogen per mole of methanol, and particle size you can see, like, 18.7 nanometer. So it's completely a heterogeneous way of production. Further, we know, like, some of the ligands, they have a very crucial role in stabilizing the nanoparticles, or it may act as internal base, or it may have certain unknown role in these hydrogen production or in most of the catalytic reaction. With this thought, we explored the ligand to hydroxypyridine, and what we have observed, like, there is a significant enhancement in the total amount of so particularly the conversion has been increased very drastically from 0.45 to 0.66 moles of hydrogen per mole of methanol. And further, we explored different type of ligands, and we try to find out what is happening here. And so we change to hydroxypyridine to methoxypyridine and even pyridine and phenol. And what we have seen, like only in this case, to hydroxypyridine, higher activity was observed. And probably this might be, we are not sure about it, but probably it is known to hydroxypyridine in solution phase, so it will be converted into pyridone form, and which acts as a internal base. Am I audible?
Yes, sir, you are audible.
Yeah, some background sound is.
Yeah, yes, sir, some noise.
Okay, no problem. Okay, so further we have utilized different type of precursors like parathymine precursor, or we have also utilized pre-synthesized ruthenium nanoparticle. And what we have observed, like in ruthenium benzene only the higher activity was observed. In fact, in ruthenium pre-synthesized ruthenium nanoparticle is very low active, and ruthenium parathymine is of intermediate activity. And this is probably because the particle size differences, although we have not analyzed it, but what we have what we believe, like the rate of reduction of these organometallic precursors into nanoparticle is playing a crucial role. And compared to ruthenium benzene and parathymine replacement is very quick and compared to benzene, so it leads to the very larger particle, and that's why probably it is a parathymine complex precursor shows lesser activity. So what we have observed, like in situ generated ruthenium catalyst is more active, and we try to find out what is happening in the solution case. And when we analyze it with 13C, and what we have observed, only formate was observed. Of course, methanol was there because it is not complete conversion, but formate was observed. And there could be a thinking like CO2 is probably getting escaped from the solution. So we analyze the gaseous part also, and what we have observed is complete purified hydrogen is only present. So our reaction is restricting only to the formate from methanol. And further, we have analyzed to find out whether the active form of the catalyst is homogeneous or heterogeneous. Of course, we did recyclability. I'll be showing that result in next one or two, after 2 slides. And but we have extensively analyzed the reaction solution, and what we have. So after the reaction finished, we perform the reaction in the presence of mercury, and there is a significant quenching. And after 5 hours of the reaction, we recovered the catalyst, and we stirred it with mercury, and we performed the reaction. And what we have observed, there is significant quenching. At the same time, the solution did not show any reaction, so it indicates like there is no soluble organometallic active component in the solution, and in fact everything is heterogeneous in nature. We further analyze the particles we observed, and what we have observed, there is a nitrogen peak also observed in XPS. And further, when we performed TZA, and we found there is a 30% loss, 30% weight loss in the particle obtained with the ligand, and compared to that obtained without ligand. So probably, and also in the CHN analysis, elemental analysis, we observed there is some nitrogen content. We are not sure about how this ligand is present in that form, but probably when we see TM images compared to the nanoparticle obtained in the absence of ligand, it was 18.7 nanometer approximately. But here you can see it's a very sharp particle size distribution, which is centered around 1.5 nanometer. So probably it is acting as a capping ligand, and it also act as an internal base. We have yet to analyze it and confirm it. Okay, so with these results, and we have also used it for ethanol and propanol dehydrogenation, and we obtained the respective carboxylates in water. This catalyst shows very good recyclability. You can see here at 130 degree, it shows very higher activity, and we did it in recyclability up to 7 cycle, and we obtained very high, in fact, 1.42 equivalence of hydrogen per mole of methanol, which is very close to our desired 2 equivalence of hydrogen per mole of methanol. So at 130 degrees. So one of the issues with this ruthenium nanoparticle is the over-oxidation, and because we are performing reaction in water, so that is one of the reason we observed in this case. And this ruthenium nanoparticle is also active for formaldehyde dehydrogenation, because that's why we are able to achieve the end product of format. In next few slides, I'll be discussing about some of the homogeneous catalysts for formaldehyde dehydrogenation. Of course, we are able to achieve complete dehydrogenation of formaldehyde using homogeneous catalysts. And formaldehyde also have very high hydrogen content. And even if we take 37% formaldehyde, it has 5-8% of hydrogen. So large number of homogeneous catalysts have been reported in this case, and because it can be achieved at lower temperature, around 95 or even up to 60 degree. And in most of the cases, you can see iridium or the nitrogen based or some of the internal bases kind of thing. Here you can see oxygen. They play a crucial role in all these cases. And we have also reported one of the pyridine methanol based catalyst for formaldehyde dehydrogenation. Using the organometallic precursor in presence of different type of ligands, and what we have achieved, surprisingly, this 2-hydroxypyridine, which was active for methanol dehydrogenation, of course, in a different way. But here, what we have observed, the monometallic monodentate ligands are more active, and what we have observed, imidazole work efficiently, and we have achieved very high activity in the presence of imidazole. You can see here the comparative results. This is without ligand and this is with ligand, so you can see observable enhancement in the activity. And we analyze the reaction system, and we try to see that how this the content of imidazole, whether it is acting as just as a base or it has some role with the complexation. So we control the reaction, and we perform reaction with 1 equivalent, 2 equivalent, and 3 equivalent of imidazole with respect to ruthenium metal center. And what we have observed, you can see like this black with the 1 equivalent, it shows a steady release of the gas. And for 2 equivalent, initially it was very high and active, and then all of a sudden the reaction ceases. And then with 3 equivalent also, it shows initially very high activity, but again reactions is at almost like 50% of activity. So we have analyzed it, and what we have found, like with 1 equivalent, it works efficiently, and it forms monoimidazole, bis-imidazole, and tris-imidazole based system. And we have analyzed the reaction mixture, and we have observed, in fact, the monoimidazole coordinated bis-imidazole and tris-imidazole system. And at the same time, we have also observed dihydroxymethanol and methane, and system for this in the in situ form. And further, we have to confirm it further. We synthesize purified complexes, and what we have analyzed through mass. And you can see here in this particular graph, and there is a very good matching with the in situ. This black one indicates the in situ, where we have used ruthenium precursor and with 1 equivalent of ligand. And this we have synthesized with 1-imidazole, so monoimidazole ruthenium parasamine complex, and you can see a very good matching with the activity. And similarly, for the base-imidazole system, we can also see this pink line and this red line. They are in very each other. So it indicates like, of course, these species are probably involved in the catalytic reaction. Further, we analyze the reaction gas released from the system, and you can see a increase in the carbon dioxide content with the increase in the reaction. And we have analyzed the reaction effluent and for 6 hours, and what we have observed, the initial hours, there is very high hydrogen to CO2 content, and which is consistent with the initial formaldehyde to formic acid conversion, where you have more hydrogen and the less formic acid to CO2 reduction, dehydrogenation occurs. But as the reaction progresses, you can see this hydrogen to CO2 ratio is coming down to almost 1:1, and which is corresponding to the formic acid dehydrogenation. So which indicates like initially all the formaldehyde is converted into formic acid, and slowly this formic acid dehydrogenation occurs. And we have performed reactions separately, and we have seen like the rate of dehydrogenation of formic acid is slower than that of formaldehyde. So this is what we have observed. And of course, when we perform reaction with mercury or without mercury, there is no change in the activity. And this homogeneous catalyst, you can see here up to 8 cycle, there is not significant loss in the activity for the dehydrogenation of formaldehyde. The ligand role is not only restricted to achieve higher activity, but it also help us to achieve long-term stability. You can see here this blue bars indicates in the presence of ligand, and this one is in the absence of ligand. You can see there is a sharp decline in the activity, while in the presence of ligand, the loss in the activity is less. So it indicates like ligand also facilitate the formation of this active form of the catalyst. With all these, and we have explored this catalyst for long-term stability, and you can see like for up to 35 hours, we have over 35 hours we have used it for long-term and the bulk production of hydrogen. And what we have observed, there is a steady release of the hydrogen gas, and still more purified hydrogen was observed compared to CO2. And we have achieved turnover over 12,000 and TOF of 5714. So these are the good numbers of what we have observed for formaldehyde dehydrogenation. So effectively, from this catalyst, what we have presumed initially, it is converted formaldehyde coordinate with the system, and this we have analyzed by mass also. And the dehydrogenation leads to the formation of formate, and further this decarboxylation forming the metal hydride, and then protein assisted dehydrogenation leads to the regeneration of this aqua coordinated complex. So with this, I came to the end of this presentation, and what we have realized that, of course, it is good to have a system which has zero carbon, but at the same time, we can use this low carbon content system for the generation of purified hydrogen, so that we can eliminate the release of carbon dioxide in the atmosphere. So this is a picture of my institute, IIT Indore, which is centrally located in the Madhya Pradesh. And I would like to thank my students in Catalysis group at IIT Indore, Department of Chemistry. And I would also like to thank the financial support from various funding agencies and instrumentation facility I've used from various part of India and in abroad also. So with this, I'd like to thank everyone for giving me this opportunity. Thank you.
Thank you so much, sir, for enlightening us with your talk. Now the session is open for discussions. Kindly ask your questions.
Can I ask you, my friend Sanjay?
Yes, Jayanta.
Yeah. It's a very interesting talk, nice presentations, and congratulations. Very nice results. I enjoyed thoroughly. Just I was wondering, the first part of your talk, that is the ruthenium nanoparticle. I mean, I guess ruthenium nanoparticles
Yes.
supported onto the backbone of whatever ligand that you are using. I mean, just I was thinking, what might be the reason that it stopped at formic acid level? Why it did not dehydrogenate again?
Yeah. So we have performed some reaction, and probably the carboxylate, because most of this formic acid dehydrogenation is not reported with ruthenium nanoparticle. Was probably that's why, and we have performed reaction even with the pure formic acid with ruthenium nanoparticle. It is not working.
It doesn't work.
Yes.
Okay.
So that's why it is.
Okay.
But of course, if we change the reaction condition, because we are not performing these reaction under reactor, so it is an open system. So
Okay.
do this reaction in high pressure reactor, that we have done long back, but it might act, but we are not sure about it.
And just a second query, not question, the same part of only ruthenium thing only, because you showed a very dramatic effect of the ligand backbone, the orthohydroxypyridine. That is very interesting actually. So I was thinking, I did not find, maybe it is in the paper you did not show. I did not see the hot filtration test. Definitely you have done, right?
Yes. So maybe.
So it doesn't show any homogeneous activity, right?
Yes. I maybe I will quickly show you that. That is one of the things that we never skip.
That's why, no one will skip in heterogeneous. Correct.
So you can see here, because to ensure that there is no homogeneous species during the reaction is developed. So that's why we perform reaction when it is very highly active in the initial few hours, and we filter it, and then we perform reaction even with the solution. So you can see there is no activity.
Solution does not have. So that it proves that you don't have any leaching of the nanoparticle in presence of the ligand, because that might be also active in homogeneous, like in the second part that you are showing. It might be active as well.
Okay. Yeah, we in fact did ICP analysis. We have not shown that result here, but there is no homogeneous species in the solution.
Okay. Yeah, I think I'm done. Thank you very much.
Thank you, Jayanta. Thank you.
Are there any more questions? Okay, I suppose not. Thank you, sir, once again for joining us.
Thank you very much. Thank you very much.
Moving on, we have with us Professor Shashank Mishra. Professor Mishra is an assistant professor of chemistry at the Claude Bernard University of Lyon 1, UCBL, France. His research interests are concerned with different facets of inorganic and metal organic chemistry, with special focus on design of molecular precursors for oxide and non-oxide nanostructured materials and understanding their transformations via solutions or vapor phase routes for different applications. He also focuses on inorganic-organic hybrid materials for diversified applications. He has published, mostly independently, over 50 research papers in peer-reviewed international journals and 5 review articles contributions to books. Sir, I would like to request you to kindly deliver your talk.
Thank you very much for your kind introduction. I hope you can hear me clearly.
Yes, sir, you are audible. We can hear you clearly, sir.
Okay, so let me share my presentation. Are my slides visible to you?
Yes, sir.
Okay, so thanks again. I would also like to thank the organizing committee of this conference. I think you need to mute yourself. All right. So yes, I would like to thank the organizing committee of this conference, and in particular to Dr. Pankaj Bharali for inviting me for this talk. So a very warm hello to everyone. As mentioned in the introduction, my talk today is about molecular pathways to inorganic nanomaterials for catalytic applications. All right. So in this bottom-up approach of the synthesis, rationally designed molecular precursors, which have a particular set of properties, are transformed into nanoscale and nanostructures materials by so-called soft chemistry method, such as sol-gel procedure or metal organic decompositions in the solution phase, or emulsivity in the gas phase. Now, in this approach, the designing of the molecular precursors, or what we call molecular engineering, is the most important aspect because a deposition process can only be as good as the precursor employed. Now, these designed molecular precursors are the starting point of the process, and therefore they influence the micro and nanostructures and of course the properties of the obtained materials. So in our group, what we do, we attempt to establish relationship between the precursors and the final materials by trying to understand what happens at interface when these molecules are transformed into nanomaterials. So over the years, we have developed a large library of molecular precursors which can be employed either in solutions or gas phase for the synthesis of nanomaterials. So in my talk, I'll be describing different kinds of materials for catalytic applications. Why catalytic applications? Because I work in an institute which is meant for heterogeneous catalysis. And as at the beginning of this session, Professor Beller, he said that we need to realign our research time to time. So, but this presentation, the main focus of this presentation is on molecular precursors. So the catalytic materials that I have chosen for this presentations, they include the atomically dispersed doped metal oxides by sol-gel procedure, and these materials are usually with high surface area and have tunable acid-base properties. So the one particular materials that I'll be showing will be the doped titania for dihydroxyacetone transformations, or the metal organic decomposition derived lanthanide fluoride based upconverting nanoparticles and their composites with TiO2 for the infrared induced photocatalysis, or these metal fluoride as unconventional support for gold catalyst for oxidation reactions, and the metal chalcogenide nanoparticles synthesized via reactive intermediates and their composites with TiO2 for photocatalysis. So I will start with the sol-gel derived atomically dispersed metal oxides for dihydroxyacetone transformation. Now, when it comes to solution phase synthesis of nanomaterials, the sol-gel procedure is the most versatile process, particularly to get metal oxide nanomaterials. And in general, metal alkoxides are the preferred class of the sol-gel precursors. However, the use of classical metal alkoxides in the sol process, in the sol-gel process, is of limited applications because of their extremely high susceptibility towards hydrolysis and the poor stability of the obtained colloidal solutions. So our work on sol-gel process, it focuses on two aspects. The first is the modification using functional alcohols with additional ether or amino functionalities. These functional alcohols not only alters the physical and chemical properties, but also due to their action as surfactants, stabilize the obtained colloidal solutions. The second aspect, it consists of developing well-characterized heterometallic alkoxides, which as single source precursors provides homogeneity of the metallic component at molecular level. Now, to elaborate further the concept of molecular engineering, I take here example of amino alcohols, which we have used for the modification of classical metal alkoxides. Now, these amino alcohols with different functionality have many properties which are useful for chemical depositions of nanomaterials. In fact, these metal amino alkoxides with their mixed oxygen and nitrogen environment are kind of good compromise in stability and reactivity between all oxygen and all nitrogen. So one can vary systematically the R substitution at alpha carbon atom to increase the volatility and thermal stability of the precursors, usually for emulsivity process. The use of fluorinated alkyl groups usually leads to further increase in the hydrolytic and thermal stability, as well as increase in the volatility of the molecules because of the weaker van der Waals forces among these fluorinated groups. Although in certain cases, the introduction of intermolecular hydrogen bonding may lead to decrease in the volatility of the precursors, but that happens rarely. Also, these fluorinated ligands may act as an in situ source for fluorine doping. So one can also make a systematic change in the density of these amino alcohols to improve the sol-gel characteristics of the resultant metal amino alkoxides. What we have found that among these amino alcohols, the metal derivatives of N-methyl diethanol amine alcohol, it behaves best in terms of hydrolysis and condensation, as well as stability of the colloidal suspension. This ligand also shows a remarkable assembling characteristics to form novel heterometallic complexes. As I mentioned previously, these heterometallic complexes, what we call single source precursors, have pre-existing M-O-M prime bonds and therefore provide greater homogeneity of the metallic component at the molecular level. For example, this novel aluminium gallium heterometallic alkoxide on hydrolysis, it gives a mesoporous group 13 mixed metal oxides with an enhanced BT surface area, which allowed us to use it as a mesoporous support for the deposition of gold nanoparticles to form effective catalytic system for the aerobic trans steel-bin oxidation reaction. One area where we are concentrating right now is the synthesis of atomically dispersed supported metal catalyst by soft chemistry method. Now, these ultra-dispersed supported catalysts with maximum atom efficiency, unique metal coordination moment, and tunable catalytic properties are an important frontier in heterogeneous catalysis. This aspect was also mentioned by the Professor Beller at the beginning of this session. However, the synthesis of these single atom catalysts remain a great challenge due to the thermodynamically driven atom aggregations, particularly under plastic conditions. So in this context, the soft chemical methods which are usually used, such as sol-gel, may provide greater stability. For example, the sol-gel synthesis of these single platinum atoms dispersed on mesoporous alumina was recently reported from a mixture of aluminum isopropoxide, the platinum salt, in the presence of a copolymer P123. As the single atoms are firmly confined within the pores of the support, the obtained dispersed catalyst will get good stability. However, the reports of this approach to get atomically dispersed supported catalysts are rather, and they are mostly limited to two metals such as platinum, gold.
Sir, you were not properly audible.
Okay, let me check my volume.
Yes, sir. Now you are audible.
Okay. So, okay, probably I need to be nearer to my mic, my computer.
Yes, sir.
All right. So I was saying that. Yes. Okay. So using these modified molecular precursors, we have recently succeeded in obtaining atomically dispersed niobium and lead within titania, having high surface area and tunable acidic properties. So the doped metal oxides display XRD peaks, which are typical of anathase titania. The absence of any XRD peaks due to niobium or lead oxides indicates a kind of high dispersions of these metallic centers. The Rietveld refinement shows that TiO2 lattice, it becomes more restrained upon doping, and like XRD, the Raman spectra also show a slight broadening and decreased intensity for these doped catalysts, and therefore suggest partial incorporation of these niobium and lead centers inside the titania lattice. The atomic level ultra dispersion is further confirmed by the high resolution STEM images, which show the absence of particles larger than 2 nanometers. So while the lead doped catalyst is ultra dispersed, the dispersion of niobium is slightly less homogeneous, as marked by the coexistence of isolated atoms and clusters of varying size. So the nitrogen adsorption, desorption isotherms of these doped samples are typical of mesoporous materials with significantly high duty surface area in the range of 250 to 350 meters square per gram. Now, the oxides of niobium and lead are well-known Lewis acids, and their dispersions within titania at atomic level boost the level acidity, the Lewis acidity of nanometric titania in a controlled way. So no surprise that these highly dispersed catalysts having high surface area show much better catalytic activity for the model reaction of dihydroxyacetone transformation into lactic acid. So the DHA consumption is about 50% for the undoped titania after around 4 hours, which increases up to 90% and 75% for the niobium and lead doped catalyst respectively. On the other hand, the lead doped titania catalyst was more selective for the production of lactic acid. Now, according to the generally accepted mechanism, pyruvaldehyde is the intermediate product that is produced by the DHA dehydration and usually catalyzed by the Bronsted or Lewis acid sites, whereas the final product lactic acid is formed by hydration of the pyruvaldehyde by the Lewis acid sites only. So keeping this in mind, one can conclude that the better DHA conversion by niobium doped titania is due to an increase in its Bronsted acidity, whereas the higher lactic acid yield by lead doped titania is due to an increase in its Lewis acidity. So as I said previously, I will not dwell in details the catalytic part. So the article, these results were recently published in an article, so interested audience can go through this article. I will now describe the MOD synthesis of lanthanide fluoride based nanoparticles, many of which find applications as the most efficient host matrix for near infrared to visible up conversion. So at the beginning of this presentation, I mentioned that the bottom-up synthesis facilitates a better control over the composition, as well as the structure and morphology of the nanomaterials. Unfortunately, this approach for the synthesis of metal fluoride nanomaterials, it remained almost unexplored, mostly due to unavailability of the suitable metallic precursors until we started working on these materials. So the most commonly used the chemical method is the metal organic decompositions of the decomposition of lanthanide trifluorostate, which is commercially available. and usually we use a temperature between 300 to 330 degrees centigrade in the presence of some capping ligand. Now, this precursor, which is commercially available, has advantage of being air stable, and as you can see, it is decomposed easily. However, the presence of water molecules is usually detrimental for the quality of luminescent materials. So, because if retained on the surface of nanoparticles, they may quench the luminescence. It also increases the risk of formation of oxofluoride phases during the decompositions. So in last few years, we have reported many anhydrous homo and heterometallic precursors that decompose at significantly low temperature to give metal fluorides-based upconverting nanoparticles. Now, for example, this sodium lanthanide heterometallic, which act as excellent single source precursors to obtain the sodium lanthanide tetrafluoride-based upconverting nanoparticles. They are, as I explained before, that they are the most efficient post matrices for the upconverting nanoparticles. Now, these precursors not only have all the elements of the final materials in right stoichiometry, but they are also anhydrous, and they also have diglyme ligand, which acts as a capping ligand during decomposition to control the particle size and to make them dispersible in organic media. Recently, we have extended this approach to lithium-yttrium tetrafluoride-based upconverting nanoparticles, which are more efficient in the UV region. And we are interested in the UV region, as I will be explaining shortly. So we and a few other groups have actually used these upconverting nanoparticles to extend the absorptions of titania in the IR region for photocatalysis. Now, since the band gap of pure titania of the anatase phase is about 3.2 electron volt, usually the ultraviolet radiation is necessary to activate it for photocatalysis. Now, the solar spectrum has about 45% of IR, which remains untapped for photocatalysis. So the one strategy to prepare upconverting nanoparticles and titania composite is to prepare core shell structure, where the upconverting core it acts as a medium to convert near infrared to UV visible light to activate titania as photocatalysis photocatalyst. Now, using this core shell strategy, we and some other groups have demonstrated a degradation of organic dye under infrared irradiation, which kind of validate the concept of transferring the near infrared to visible light to activate TiO2 for photocatalysis. Recently, we have used another strategy where these upconverting nanoparticles were embedded uniformly in the transparent metallogel of titania. Now, of course, the amount of as the amount of nanoparticle it increases, the transparency of the gel it decreases, but it does not have any drastic effect on the uniform distribution of the nanoparticles. Now, as the metallogel was obtained without using any organic ligands, the air drying of these nanoparticles embedded metallogels lead to homogeneously dispersed composites with high surface area and the desired crystalline phase of the two components, that is the anatase phase for the titania and the hexagonal or the tetragonal phase for the sodium gadolinium tetrafluoride or lithium yttrium tetrafluoride respectively. Now, unlike the core shell structure, the titania upconverting nanoparticle ratio in these metallogels can easily be varied, and the production of these nanocomposites can be scaled up significantly. So we are in fact currently making efforts to improve further the efficiency of these photocatalysis by using a wider range of solar spectrum, for example, by introducing in metallogel a suitable luminescent molecules that absorb in the IR regions and therefore allows a broad absorptions by acting as an antenna. So we have also used this sodium yttrium tetrafluoride as unconventional support for gold nanoparticles and studied their catalytic performance in oxidation reaction. Usually metal alkoxides are the support used for these gold nanoparticles because in oxidation reactions, the activation of molecular oxygen is of utmost importance. And the support is said to be involved in dissociating molecular oxygen at the perimeter site of the gold nanoparticle. To some extent, supports such as metal organic frameworks or carbon or zeolites have also been employed, but never metal fluorides. So, as I explained before also, under different conditions, this heterometallic precursors, it gives two different crystalline phases of sodium yttrium tetrafluoride, that is alpha and beta, in phase pure phase pure manners, and these two phases have a very different structures as well as surface characteristics. So we use them as a support for the deposition of gold nanoparticles. Now these alpha and beta phases, which as I said that have different surface properties and BT surface area, behaved differently during the deposition of PVA protected gold nanoparticles of about 5 nanometer size. So whereas a loading of about 0.7% gold took more than 12 hours in the case of beta phase, the similar loading could be achieved within 1 hour in the case of alpha phase. Now the core shell XPS spectra in the gold 4F region show binding energy between 82.4 to 83.4 electron volt, which can be assigned to the metallic gold. What is interesting here is that we observe splitting of the characteristics 4F bands for gold deposited on the beta phase. So the prominent bands corresponds to the core gold atoms, whereas the bonds with low intensity, they are due to the surface gold atoms at the gold PVA interface. So this indicates that when deposition of the PVA protected gold nanoparticles takes a longer time, which in fact is the case for beta phase, washing the sample with water is not sufficient to remove the PVA ligand entirely. So this slide summarizes the results on the use of gold on sodium yttrium tetrafluoride catalyst for the aerobic epoxidation reaction of steel transbeam in the solution phase. So in terms of trans-steel oxide yield, the catalysts are at par with the World Gold Council's reference catalyst, that is gold on titanium, but they are better than the reference catalyst when it comes to steel bin conversion. And the another observation is that the doping of the support yttrium sodium yttrium tetrafluoride with gadolinium eliminates the induction period and also enhance the catalytic activity as indicated by the large TOF values. However, it decreases the selectivity. Generally speaking, the composition and chemical nature of the support have little effect on the intrinsic epoxidation activity of the catalyst, but rather influence the overall reactivity patterns via mass transfer limitations. For the CO oxidation in the vapor phase, the gold on sodium yttrium tetrafluoride behaved on expected lines and exhibited a poor activity as compared to the gold catalyst supported on reducible metal oxides. There is a general consensus that the neutral gold particles alone cannot activate the oxygen-oxygen bond without some assistance from the support in terms of charge transfer process or involvement of specific sites at the interface. Although CO oxidations can be accelerated to an extent by the presence of hydrogen, overall, even with hydrogen, these gold catalysts on metal fluorides are less efficient for activating oxygen than those supported on metal oxides. So these are on expected lines. I will now switch over to metal chalcosinides nanoparticles and their applications in the field of photocatalysis. So the most important aspect of this work includes our attempt to trap reactive intermediates and characterize them thoroughly. Now, this has great significance in comprehending molecules to nanoparticles transformation mechanism and also to optimizing the synthetic conditions. Now, there are several methods known in the literatures for the solution phase synthesis of metal chalcogenides, and almost every method it uses surfactant to control the particle size and make them dispersible in organic media. Since our objective was to use these nanoparticles in photocatalysis after combining them with TiO2, we wanted to develop a surfactant-free, low-temperature synthesis of metal chalcogenides to avoid any structural and morphological changes in titanium. So using non-silylated chalcogenoethers, particularly the ones which have facile decomposition mechanism, we have isolated many precursors with low thermal decomposition temperature, and these usually yield binary and ternary metal chalcogenide nanoparticles at much lower temperature and in a controlled manner. More importantly, use of these non-silylated chalcogenoethers allowed us to isolate and characterize the reactive intermediate species during the transformation of molecules to nanoparticles, and therefore to understand in a better way what happens at interface when these molecules are transformed to nanoparticles. Now, for example, this trapped heterometallic molecular complex of this composition is highly unstable and reactive. So its thermal instability is confirmed by the thermogravimetric analysis, which shows that the compound decomposes below 100 degrees centigrade. The molecule is also kinetically unstable, as indicated by the DFT calculations, which shows a very low homo-LUMO band gap. On living in air, the compound gives a black powder in a few hours, which is composed of copper, silver, selenide, and also some impurities of silver selenide. The isolated compound is quite unstable even when kept at low temperature and in argon in inert atmosphere, and it decomposes within 1 to 2 days, apparently due to the formation of metal selenides. So the stability of these molecules can be tuned to an extent by judicious choice of chalcogenoethers. So thus, by replacing selenium with sulfur, one obtains a structurally similar compound, which is kinetically more stable, as indicated by the homo-LUMO gap, band gap of about 3.1 electron volt, as well as the fact that it can be kept in a closed schlank for several weeks without any decompositions, although it still decomposes at low temperature at about 120 degrees centigrade. When we replace ditertiary butyl chalcogenides with dimethyl chalcogenides ligand, for which there is no beta hydrogen elimination mechanism, the obtained molecules are both thermally as well as kinetically stable. So what is interesting is that when the precursors with ditertiary butyl selenide is taken in a coordinating solvent such as THF, or even brought in contact with the vapor of the solution, it shows a reversible thermochromism. It changes its colors from blue to green with increase in the temperature, which is confirmed by the curve showing a decrease in the decrease in the blue to green ratio with increase in the temperature. And so this is simulated absorption spectra of this complex, which show that significant changes happens with change in the temperature for this. So we attributed this behavior to the coordination and discoordination of the solvent molecules with the copper centers. In the X-ray structure, the tetra-coordinated copper center has two axial positions which are vacant in the absence of any significant interaction between copper and selenium. And this can coordinated and discoordinated by THF molecules as a function of temperatures. The ditertiary butyl analogues does not show any thermochromies. It has, as can be seen, a significant interaction between copper and sulfur, which might prohibit the coordination of solvent molecules at copper centers. The dimethyl chalcogenide analogues also do not show any thermochromies because these have intramolecular silver-silver interactions in the extended structures, which lead to its structural rigidity. Now, as we all know, titanium dioxide is the most widely used UV photocatalyst. As I explained, mentioned before also, however, it has two major drawbacks. One is that it has a band gap of about 3.2 electron volt, which limits its applications in the UV region. And the second is that a large number of electron and hole pair recombination dissipates energy in the form of heat and light, which reduces its efficiency. So our idea to improve its photocatalytic efficiency was to couple it with narrow band gap metal chalcogenides nanoparticles, which would not only extend the absorption region in the visible region, but also facilitates efficient charge separation and thus reducing electron hole recombination. The mild conditions employed here to obtain these metal chalcogenide nanoparticles facilitates the synthesis of these composites with the TiO2 without changing the morphological or structural characteristics of the titanium counterpart. So for this particular nanocomposite, the TEM and EDX analysis confirms the presence of intimate mixing between the two components. Now, while the BET surface area is slightly decreased for these composites as compared to the titanium alone, the diffuse reflectance spectra, it indicates that the absorptions in these composite is extended on increasing the metal selenide percentage. For example, lowering in the band gap from 3.15 for pure titanium to about 2.40 for the sample with 10% of copper silver selenide is observed. So these nanocomposites were tested for photocatalysts as photocatalyst for the photodegradation of formic acids under UV and visible lights. Now, generally speaking, the composites with low content of the metal selenide show better UV-induced catalytic activity in comparison to the P25, which is a kind of well-known benchmark for the photocatalysis. The enhancement in the photocatalytic activity can be explained by the formation of semiconductor semi-metallic heterojunction in these nanocomposites as established by the DFT calculations. And this allows a better charge separation of electron and holes, which results in their better photoactivity. So I must be mindful of the time, so I'm not going to dwell further on these catalysts. A majority of this work has been published recently, and the interested audience may go through these articles. In the end, I would like to congratulate the Department of Chemical Sciences of Tezpur University for organizing this wonderful conference. I'm fortunate to have collaborations with the research group of a very dynamic Professor Nayanmani Gogoi of this department, and I hope my association with Tezpur University would not only be sustained, but also be made more profound. I take this opportunity to thank all my students and these people who have been instrumental in this research. I'm particularly thankful to all these institutions for providing me a platform to carry my research work and all their financial support. And thank you all for your attention.
Thank you so much, sir, for your intriguing talk. The session is now open for discussions. Kindly ask your questions. I believe there are no questions. Thank you so much, sir, for joining us.
Thank you. Thank you.
Thank you, sir. Moving on, we have with us now Dr. Jongbyom Na. Dr. Na is working as a postdoctoral research fellow at the National Institute for Material Sciences and as a visiting academic at the Australian Institute for Bioengineering and Nanotechnology, the University of Queensland. His major research interest is in the design and synthesis of functional nanomaterials, organic inorganic hybrid materials, and energy conservation storage applications. Recently, he is focusing on the development of nano-architectured polymeric inorganic materials for electrochemical energy storage, electrocatalysis, and environmental applications. Sir, I would like to request you to kindly deliver your talk.
Thank you for your introduction. Nice to meet you. My name is Jongbyom Na. Can you hear my voice?
Yes, sir. Yes, sir, we can.
Okay. So nice to meet you. My name is Jongbyom Na, and then I'm a research fellow of the Professor Yamauchi's group in the University of the Queensland. And then firstly, thank you for these invitations of this great conference. And then today I will do this presentation instead of the Professor Yamauchi because his schedule has been accidentally changed. So we are very sorry, and then please understand these situations. So the main title of today's presentation is the material space tectonics, a conceptual paradigm for the creating second generation porous materials. So this is the historical table, which is more than 30 years of the porous materials. And then after the first discovery of the mesoporous silica, which is the MCM41, we can see the very highly improved and then progress in the porous materials. And then nowadays, the mesoporous metal can be synthesized by the soft templating approaches. And then this is the very basic concept of the soft templating. And then we can use the surfactant that can be self-organized to make the ordered structures in the aqua solutions. And then as shown in these images, we can make the ordered hexagonal structure and the water domain, and then the water domain is existed between the micelles. And the inorganic materials can be synthesized in these aqua solutions. And then after the removal of the templates, we can prepare the porous materials, which is general principle synthesis. So recently we are thinking about material space tectonics, which is the Lego inspired materials design. And then based on the concept of the space tectonics, we are using the several kinds of the inorganic materials. And then they can be organized with the surfactant to make the one-dimensional, two-dimensional, and then zero-dimensional material structures. And then we need the additional integration of the materials to apply to the practical applications. So among the various materials, the porous materials is one of the high potential materials for the space tectonics with the specific functions. And then I would like to introduce the two kinds of the functional porous materials in this presentation, which are the mesoporous metal and then the porous carbon materials. Furthermore, the practical application of these materials will be introduced as well in these presentations. So firstly, the mesoporous metal have many profit due to their porous structure and then the metallic properties, and then which are the high electrical conductivity and then electrochemical properties. For this reason, the mesoporous metal are being used for the various applications such as the energy storage, catalyst, and then electrochemical and the optical sensors. So to synthesize the mesoporous metals, we use the two kinds of the reactions that are chemical reductions and then the electrochemical reductions. So through the chemical reduction method, we can synthesize the mesoporous metal nanoparticles. On the other hand, we can synthesize mesoporous metal with forming the film formations onto the conductive substrate directly by using the electrochemical reduction method. Then there are three main synthetic strategies of the mesoporous metals, and then hard template, soft template, and then the solution phase approaches. Generally, for the hard templating method, at the time it's a silica and then carbon materials are mainly used as a template. But in the soft templating method, the organic or the polymeric the materials such as the liquid crystal, surfactant, or the micelles are used as a template materials. Among them, the soft templating method with the micelle is mainly used to synthesize the mesoporous metals because it is easy to remove, and then the template, then the simple process. From this slide, I would like to introduce one of the soft templating methods by using the polymeric micelles. To make the polymeric micelles, we use the block of polymers, which can be designed and then synthesized with the different polymer the molecular structures. And then they can form the micelle structure in the aqueous solutions because of the hydrophilic and then hydrophobic polymer chains. Depending on the molecular weight of the block of polymer and then the concentrations, we can make various assembled structures such as the hollow, nanotube, and then nanoporous structures. This slide is showing the process of the mesoporous metals by using the block polymer micelles. So the mesoporous metals are hard to synthesize, and then it is impossible to make it with the normal approach. So that's why we use the polymeric micelle, and that shows the two different the hydrophobic and then hydrophilic polymer molecular structures. And through the micellization of these block of polymers, the hydrophobic domains is located to the core of the micelles, and then the hydrophilic domain is located to the surface of the micelles, with the interacting to the water molecules. And then after dissolving the metal precursor, the metal ion can be attached to onto the surface of the micelles. And then as shown in these right side images, the metal ion and then micelle complex are well dispersed in the aqueous solutions. And then by using this complex, we can synthesize the mesoporous metal film and then particles with the reducing of the metal ions by using the electrochemical and then chemical reduction method. So from this slide, I would like to introduce the details of the electrochemical deposition method for the to synthesize of the mesoporous metals. So firstly, the block of polymers are dissolved into the organic solvent, and then the water and the ethanol are dropped to the polymer solution with the metal precursors for micellization of the block polymers. After micellizations, the metal ion are attached to the surface of the micelles, and then through applying the voltage by using the electrochemical workstations, we can prepare the homogeneous film with the homogeneous micelle solutions, and then the metal framework are synthesized by using the electrical voltage. And then after removing the micelles, we can prepare the mesoporous metal films. Furthermore, we can control the pore size by using the swelling agents. The hydrophobic organic compounds are used to swelling agents. They can penetrate into the core of the micelle where the hydrophobic polymer chains is located. And then through the penetration of these organic molecules, the size of core increase by swelling of the micelles. As a result, we can control the size of pores by the different volume of the hydrophobic compounds, as shown in these SEM images. And then this is another way to control the pore size. As I mentioned the previous pages, during the micellizations, the high molecular weight of polymers can form the larger size of the micelle than that of the low molecular weights. So that's why we can control the pore size by the different molecular weight of the block of polymers, as shown in these SEM images and then pore size distributions. So through this electrochemical deposition method, we could prepare the various mesoporous metal films. So among them, we synthesize the mesoporous lucene film for the supercapacitor applications. Generally, lucenium has been oxidized to improve the electrochemical redox properties. So many researchers have used the thermal oxidation method. However, they can occur the over-oxidation of the materials, and then it is hard to control the oxidation level. So for this reason, we use the electrochemical surface oxidation method, which can control the degree of the oxidation of the materials. So after preparation of through this method, after we can synthesize mesoporous lucenium and lucenium oxide films, and then they shows 17 times higher specific capacitance than that of the non-porous lucenium films. And then according to these results, we can expect that this simple and then well-controlled electrochemical deposition method can be applied to the electrode materials for the energy storage applications. In addition, mesoporous copper films were also synthesized through this electrochemical deposition method. Recently, we realized that the mesoporous structure can enhance the surface, enhance Raman spectroscopy properties, which is a source, due to their high surface area and the mesostructures. So through this control of the pore size, we could optimize the source properties and then the highest search sensitivity were shown with small pore size and then a small gap between the nanostructures. And furthermore, now we are applying this method to the semiconductor materials as well. And then we successfully synthesized the mesoporous semiconductor film by using the same approach as and then apply to the photodetector applications. From this slide, I would like to introduce the mesoporous catalyst. So as you know, the ethylene, which is the natural hormones, can be produced from the green groceries, and then it ripens them too fast. So for this reason, the effective removing of ethylene is the most important point to enhance the storage life of the green groceries. So to solve these problems, many catalysts have been developed, such as nanopowder and then catalyst with scaffold. But the nanopowder's catalyst shows very high catalytic properties and a high surface area. However, they are toxic because of their size of the particles. On the other hand, the catalyst with scaffold, they are very stable and non-toxic, but their catalytic properties and then surface area is very low. So to enhance the catalytic properties and then stability, we planned to combine the advantage of these two kinds of the catalyst. Firstly, the mesoporous silica layer is coated onto the two kinds of the scaffold for high surface area. And then the platinum nanoparticles are synthesized into the inside of the mesoporous silica layers. The mesoporous silica layers, the mesoporous silica can increase the surface area, and then the platinum nanoparticle can enhance the ethylene oxidation properties. And then as shown in these rotating TEM images, the platinum nanoparticles have been well located in the mesoporous silica layers. Interestingly, they show the high performance of the catalytic properties comparing to the commercial available catalyst. To confirm the possibility for the commercialization of these mesoporous catalysts, the preservation experiments were proceeded with the prototype devices. And then we proceeded this experiment of the preservation system with collaborating with the NBC mesh tech companies. And there are two kinds of the experiments of the preservation system by using the flowers and then fruits. Then the prepared mesoporous catalyst have greatly improved the storage life of the flowers and then fruits through the effective ethylene oxidation reactions. As a result, we can confirm that these mesoporous catalysts have a very high potential for the commercialization and then practical preservation system. From now on, I would like to introduce the porous carbon materials. Recently, our group is focusing on to the metal organic framework derived carbons. The metal organic frameworks consist of the metal ion and then organic linkers, and then those the organic linkers can be used as a carbon source. And so we have been synthesized various MOF-derived carbon to make the nano-architectured carbon materials. So as mentioned in the previous slides, the MOF is one of the most fancy materials in the research field because of the various advantages, such as facile in the synthesis process, and then large surface area, and then controllable morphologies, and so on. In our group, we have designed and then synthesized new nano-architectured MOF-derived carbon materials by the new strategies such as polymer coating, surfactant control, and then etching process. Through these new strategies, we could synthesize the various nano-architectured carbon materials. And recently, we have synthesized a carbon aerogel with the MOF. Firstly, the polymer and then MOF hydrogel are synthesized through the gelation method and through the freezing dry and then carbonizations. The carbon aerogel are finally synthesized with the large scale. The synthesized carbon aerogel show a large specific surface area by forming 3D network pore structures. And then finally, we applied this carbon aerogel to the water purifications, that is organic solvents adsorptions. Then they shows a higher adsorptions and then recyclability in the various oil and then organic solvents. So through this result, we can confirm that the various nano-architectured carbon materials have a high potential for the mass production and then environmental applications. And then this is another example of the MOF-derived carbon materials. The F127, which is the 3 block of polymers, and then they can self-assemble to the micelle with the dopamine in the aqueous solutions. After adding the GIF8, which is the one of the MOF, the micelle with the dopamine are self-assembled onto the surface of the GIF8, and then GIF8 and the polydopamine composite particles are synthesized through the polymerization of the dopamines. Finally, through the carbonization process, the multiporous carbon, including micro, meso, and then macropores, were successfully synthesized, as shown in these SEM and TEM images. So after synthesis of these multiporous carbons, we could confirm the multiporous structures through the nitrogen gas absorption, desorption isothermal analysis. And then as shown in these data, the mesopores are shown in these multiporous carbon materials. And then this multiporous carbon shows a high specific capacitance than that of the microporous carbons, as shown in this cyclophotometry and then carbon-static charge discharge curves. And then this multiporous carbon shows a higher capacitance retentions that can demonstrate the electrochemical advantages of these multiporous structures compared to the general microporous structures. So according to this result, we expect that the multiporous carbon materials can be applied to the practical energy storage applications. From this slide, I would like to introduce the different porous carbon materials without the MOF. Not only mesoporous metal, but also carbon materials can be synthesized by the same approaches by using the polymeric micelles. And then this is the one example of this kind of the materials. And then we put the dopamine in this system. After polymerization of the dopamine and then the carbonizations, we can prepare the porous carbon materials as shown in these images. Furthermore, through these approaches, we can synthesize the porous materials with the different materials such as the metal oxide or carbon and so on. As shown in these SEM images, the mesoporous carbon spheres have been successfully synthesized, and then we can control the particle size and the pore size by the reaction conditions such as concentration and then temperatures. After synthesis of the mesoporous carbon materials, we tested the supercapacitor properties by using these materials. The important point that we can control the pore size by the changing of the molecular weight of the block polymer, which is I already mentioned the previous page in the mesoporous metal part. The size of the micelle can be controlled by the molecular weight of the block of polymers, as mentioned in the previous part. And then, as shown in these figures, the capacitance can be controlled by the pore size. And then through this controlling of the pore size, we can optimize the specific capacitance. And then we confirm that the specific pore size is preferred for the spot capacitor properties. And then next challenge is the controlling the dimensioner of the mesoporous materials. If we can control the assembly of the micelles in particular directions, we can synthesize various dimensional materials. This is one example of the 2D mesoporous carbon materials. We use the MXene as a carbon precursors. However, they are very strongly stacked each other, and then this structure reduces the surface area of the materials. So that's why we need to keep the high surface area even after carbonization. So we put the micelle to the interior space of the MXene to increase the surface area. After carbonization, we can make 2D mesoporous carbon with the interior of the MXene. And then after removal the template, which is micelle, we can prepare the hybrid 2D structure as shown in this figure. And then we can keep the high surface area through the mesoporous structures. Further, and then we also can keep the high conductivity from the sp2 carbon, which is derived from the MXenes. And furthermore, we applied these materials to the spot capacitor applications, and then they show the high capacitance, and then the capacitance can be well maintained in the different current density as well. This approach can be extended to the other 2D materials, which are graphene oxide or the other inorganic nanosheets. There is a strong attraction between the micelle carbon source complex and then graphene oxide, because the surface of the graphene oxide is hydrophilic. So that's why the micelle complex is well attached, and then they have been self-assembled onto the surface of the graphene oxide. And then after carbonizations, and then removal the template which is micelles, we can prepare the 0D 2D hybrid structures. And then as shown in these SEM and the TEM images, the 0D spheres are well attached and then self-assembled onto the surface of the 2D materials. So in these presentations, I have introduced the synthesis of the mesoporous metal and then carbon materials with the various nanostructures. And then these polymeric micelle synthesis methods can be applied to the other elements, materials as well. So finally, I would like to thanks to our group member in the University of Queensland, and then the National Institute for Material Science in Japan as well. So this is the end of presentation, and then finally I wish you productive research with outstanding ideas, and then with keeping your healthy life as well. Until the end, thank you for your attention.
Thank you, sir, for your informative presentation. And now we shall have some interactive session. Some questions. Okay, I suppose there are no questions.
Yeah.
So thank you, sir, once again for joining us today.
There is a question here.
Okay, sir, there is a question.
I just wanted to know, in your porous carbon, the capacitance is not as high as what is expected in what is reported in the literature. I expected it much more than that.
Yeah.
In your porous carbon,
Yeah.
the capacitance is only around 230 farads per gram, but I expected it much more than that.
Yeah. So wait. So for example, this kind of the carbon, mass-produced carbon, and then this kind of the mass-produced carbon as well. But we use the carbon source is not only the MOF, but also we use the polymer, which is the polydopamines. So polydopamines, after carbonization, in the carbon materials, we can dope the nitrogen inside of the particles. So as you mentioned, the only carbon materials is not high the specific capacitance, but the nitrogen doped carbon and then other atoms can doped inside of the particles. We can improve the specific capacitance, and then these porous carbon materials, and then as you know, the only microporous carbon is the surface area is the highest. However, their specific capacitance is very low because of the ion diffusion property is very low. So that's why we designed the structure with the multiporous carbon to improve the ion diffusion and then ion redox reactions inside of the supercapacitor. And then the high surface area is not only the definitional the points, because the dependent to the application, but the porous structure and the nanoarchitecture structure is dependent to the application. For example, only microporous is the good properties in some kinds of the application, and then mesoporous structure is good for some kinds of the application. So that's why we should design of this porous structure to improve, and then it's very suitable structure for the applications.
Okay, so what is the pore size that you measured? Have you measured any pore size distribution in your carbon?
Yeah.
Okay, so that is around 6 nanometers, huh?
Yeah.
6 nanometers.
Generally, only GIF8 carbon is the microporous. Their surface area is higher than this multiporous carbon, but their specific capacitance is lower.
Okay.
That is the reason, yeah.
Normally in carbons, the pore size is expected to be between 4 to around 4 nanometers to give a good capacitance. That's what I understand from the literature.
Yeah, that is a good point, because that is why we need to control the pore size. Yeah.
Correct. Okay. Thank you.
Thank you.
Do we have any more questions?
Can you show me your first slide? I missed your email address.
Maybe you can see in my information, I already mentioned the email. Maybe. Can you see that?
I don't know. I missed it actually. Is it there in your first slide or somewhere?
Maybe in slide unless there's no email address. So, okay.
Or maybe in your publications I can get it?
Pardon?
From your publications I can get it?
Yeah, it's possible. Yeah.
Yeah, okay. So I'm interested in this area, so I will get in touch.
Okay. Thank you.
Thank you.
Any more questions? So I guess that's it. Thank you, sir, for joining us today.
Yeah, thank you.
Yeah, so Dr. Na was the last speaker for this technical session, and I would like to thank all the speakers for their fascinating talks. And now we shall be moving forward towards the oral presentations by the participants. Starting the oral presentation, the first presentation shall be given by Parikshit Gogoi from the Department of Chemical Sciences, Nagaon College.
Am I audible? Am I audible?
Yes, you're audible.
Okay. So please allow me to say. Okay. Good afternoon to all. First of all, am I audible? Am I audible?
Yes, sir. Yes, sir.
Okay. Good afternoon. First of all, I'd like to thank the organizing committee and the convener of this conference, Dr. Bharali and Kusum, Dr. Kusum, for giving me a chance to share my research. So today I'm Dr. Parikshit Gogoi. I'm working as an assistant professor of chemistry in the department of chemistry in Nagaon College. So today I will share some of my works that I published in recent years in Elsevier. So my topic is metal frameworks, Fenton activities towards organic pollutant remediation. So as you know that the ever increasing pollution of water and soil and different industrial, agricultural, domestic activities due to has been a major concern with the respect public health due to the recalcitrant organic toxic organic pollutants that is present in the wastewater treatment plants. So effluents from these plants have very toxic effects, and it is really necessary to demineralize all the organic pollutants. So, till now, lots of methods for wastewater treatment has been adopted, like absorption, photocatalytic degradation, ion oxidation processes. So among these advanced oxidation processes, like Fenton is one of the important process recently gained interest to the scientific community. So if you look at the Fenton chemistry, so that it is a reaction of iron 2 plus hydrogen peroxide from this radical by catalyzed by Fe2 plus ion. So actually, these waste radical ions are responsible for degradation of different kinds of organic pollutants diet. So, if you like visualize the Fenton reactions, then you can divide it into homogeneous and heterogeneous processes. Since from long back, yes, this inception, invention in 1894 by Fenton, homogeneous catalyzed reactions are reported by different researchers in the past. But due to some advantages of homogeneous catalyzed reactions, nowadays heterogeneous catalyzed reactions are very much important. So, what are the importance? If you looked at the importance, actually it stays in different phases, so it is very easy to separate from the reaction mixer, and it worked in like in normal conditions. In general, actually, Fenton reactions is takes place in within the range of pH 2 to 3. So if you look at the like reaction mechanism, Fe2 plus is responsible for the degradation of H2O2 to produce OH radicals, and this then Fe2 plus is converted to the Fe3 plus, and this Fe3 plus again react with hydrogen peroxide to again come back to the original, that is Fe2 plus, and these actually during this process OH radical is produced. This OH radical is responsible for the degradation of different kinds of organic pollutants. So here actually today I'm going to discuss about how Fe3O4 magnetite was prepared in our lab, and putting of these iron oxide materials and giving different supports by using carbon components of fullerene and by using some mixed metal oxides. So the first component first composite we prepared is beta cyclodextrin coated Fe3O4 nanocomposites. So here what we did, if you looked at the synthesis method, it is very simple method for preparation of iron oxide nanoparticles, and if you took Fe2 plus and Fe3 plus salts and stirring for 24 hours by with the addition of ammonium hydroxide at pH 8 to 10, then you will have FeOH3 precipitation. And then if you keep it for 100 degrees centigrade for 12 hours, then it will convert it to the Fe3O4 magnetic nanocomposites. So if you look at after preparation, actually we did extensive characterization of our products, and if you look at the SEM and TM images, like it is the size distribution is around 10 nanometer. So we did FTR spectroscopy and XRD and VSM analysis for this beta CD coated iron oxide nanocomposites, and it confirms that beta CD coating is confirmed above the magnetic nanoparticles. So if you looked at the activity or degradation studies of heterogeneous phantom like reactions, we studied areochrome black tea degradation. So for areochrome black tea degradation, if you use iron oxide only Fe3O4 nanoparticles, then it will within 1 hour it will degrade only 65% of the areochrome black tea. But after after coating of the materials, this beta CD coated Fe3O4 nanocomposite, it will be up to 90% conversions we get. So actually for mechanistic pathway, degradation pathway, we have proposed based on our LCMS studies of the intermediates that is formed during the reaction. Actually, initially during this degradation reaction, different kinds of different small molecular weight compounds are formed, and finally it will demineralize carbon dioxide and carbon dioxide and water. Actually, this work we published in 2019 in material chemistry and physics. So after coming to the next our component.
Sorry to interrupt you, sir. So, but you have 2 more minutes left.
Okay. Next, if you next we prepared we have given support to this iron oxide nanoparticles, and we made the coating of beta CD coating of this fullerene and Fe3O4 nanoparticles, and we studied this degradation. We studied the heterogeneous phantom-like reactions for degradation of alizanes. So the same co-precipitation method is used for this preparation, and here again we use fullerene for making the composition. So I will skip the these slides, and if you look at the reusability of the catalyst, actually these catalysts are very much stable and it retain its activity up to fifth cycle after reuse. So this work we published in 2017 in RSC Advances. So the third component, we actually tried to make bimetallic metal oxide mix, metal oxide composites, Fe3O4 cerium dioxide composites. Here we use the cerium nitrate and Fe2 plus and Fe3 plus salts for making iron Fe3O4 cerium dioxide composites. And after precipitation of these salts to respective hydroxides, and after that calcination at 500 degrees centigrade, we have that light yellow colored Fe3O4 CO2 nanocomposites. And again, here the particle size is around 10 nanometer in range. So here for this catalyst, we studied our degradation reaction for catechol degradation, and here also we are getting very nice results. And after 1 hour, actually all the catechol molecules we are taking, it is demineralized to the carbon dioxide and water. So this is the scheme of that mechanistic aspect of H2 activation by this Fe3O4 cerium dioxide nanocomposite material in acidic conditions. So, and for this catalyst also, we are getting very good stability against these phantom activities. And after fifth cycle, we are getting 93% activity. Retain activity is 93%. So this article we published in Chemical Engineering Journal in 2017. So now I can go for the conclusion. Actually, we prepared iron oxide, beta-cyclohexane coated iron oxide, fullerene iron oxide composites, along with the Fe3O4 and CO2 composites. All these composites do very good catalytic activities against the degradation of different dyes and phenols. So these are some publications, recent publications from our group in 2019, and these are some recent publications of our group from 2020. Actually, we are working on different fields like nanoparticle synthesis and then biomass chemicals and hydrogel preparations in our lab. So lastly, I'd like to acknowledge Professor Jyoti Borani, Department of Chemical Science, Leicester University, Professor India, Monia, from Raleigh for giving opportunity to share my research. And I thank collaborators, Singlia joined us on the team of Korea. Finally, I'd like to thank my students, Sristi Priyanka, Precious, and Rahul Ganpai for his constant support. Thank you. Thank you so much for your kind attention. I'd like to have some questions.
Are there any questions? Okay, I suppose there are no questions. Moving on, we have Priyanka Mani Sakya from the Department of Chemical Sciences, Tezpur University. Priyanka Mani, you are requested to present your presentation. Kindly take 7 minutes.
Okay, Exeter. Am I audible, Exeter?
Yes, you are audible.
Okay. I'm not able to share. Okay.
I think now you will be able to share. Yes, kindly go forward and kindly try to wrap up within 7 minutes.
Okay, thank you, Dixita. Good afternoon, everyone. I'm Priyanka Mani Soika, working under the supervision of Professor Sopan Kumar Doloi. On behalf of this oral presentation, my topic is calcium copper titanate and efficient perovskite-based photocatalyst. So, these are the contents. As we are shifting towards modernization, there is a rapid development of industrialization and urbanization, which ultimately affect the ecosystem by discharging toxic elements and pollutants into the natural water cycle. Dye is one of those toxic elements. They somehow enter our food chain, causing many carcinogenic diseases. They enter photosynthesis to the plant species. In aquatic animals, they increase the level of danger to the life of them, and in environment, they increase the aqueous toxicity for demanding chemical oxygen demand. So, as a part of waste management system, finding a sustainable approach to degrade those toxic elements is very urgent need. Recently, the oxidation process by semiconductor-based photocatalysts has an emerged field. The photocatalytic material can be excited by photons and generate electrons and holes, which ultimately able to reduce the pollutants. Among photocatalysts, titanium dioxide, cadmium sulfide has been widely investigated. But there are some disadvantages, like they have a large band gap and they need only UV region to its activity. Among various photocatalysts, perovskite-based photocatalyst has unique photophysical properties. For example, they have long light absorption abilities, they enable high surge carrier mobilities, they have long diffusion length, and they have tunable band gap. Due to its various advantages, they can be applied in the field of LED preparation, photocatalyst preparation, solar cell preparation, and sensor and also capacitor preparation. So, in the family of perovskite family, calcium copper titanate has gained much attention in crystallographic studies. CCTO occupy on a cubic structure where A site is shared by calcium and copper and B site is shared by titanium for positive ions. They have some distinct photophysical properties. The material is environmental friendly and also easy to prepare. So in our work, we have prepared calcium copper titanate and its derivatives through citrate precursor method, where calcium carbonate, copper chloride dihydrate, and titanium dioxide was taken in the molar ratio of 1:3:4, and citric acid was added to the solution, which acts as a complexing agent. The light color solution was further stirred at 80 degrees centigrade to form a gel-like compound, which was further calcinated at 1000 degrees centigrade at a heating rate of 10 degrees centigrade per minute to form the required perovskite structure of the photocatalytic material. So, in my photocatalytic experiment, I used a 20-watt white LED light as a visible light source. Since LED has many advantages, like they are environmental friendly, and I also used a 100 ppm rhodamine blue dye stock solution where 50 mg of the catalyst was added to the solution. Then the solution was stirred in dirt to attain adsorption-desorption equilibrium, and at certain interval 5 ml of the solution was taken out and the dye content of the solution was analyzed through UV visible spectroscopy. For identifying the structural analysis, powder XRD characterization was taken out, where we have found the 220 plane, 400 plane, and 422 plane indicate the cubic structure of the material and its composition. Moreover, the crystallite size and the crystallinity of the material was also calculated by using powder XRD spectra, where we have found the composition with X equal to 1 has a better crystallinity of 10.6%. To identify the IR active bond formation, the material was studied with FTR spectroscopy. The absorption peak at 463 centimeter inverse is attributed due to the TI-OTI bond. The absorption at 3430 centimeter inverse is due to the OA stretching frequency, and the absorption is at 525 and 606 centimeter inverse is due to the copper oxide and calcium oxide bond, respectively. The morphology of the material was also studied through SEM analysis, where we have found that the material has a polyhedral shape structure having a diameter of 1 micrometer. EDX analysis was also carried out to identify the elemental information of the material and its composition. The presence of calcium, copper, titanium, and oxygen in the host material was observed in these images. So the band gap energy of the specimen was also studied through torque plot method, where we have found that the composition with X equal to 1 has the lowest band gap of 1.93 electron volt. And the BET study was also carried out for the specimen with composition X equal to 1, where we have found that the pore volume and surface area of the material was 0.024 cc by z and 3.009 m by z square, respectively. In the BET isotherm indicate that the material was inhibited with a type 3 isotherm. Then after illumination...
Sir? Oh, yeah, you have 2 minutes left, right?
Okay. So after illumination of 6 hours, we noticed degradation efficiency to a value of 87% for CCTO and 99.7% for CCTO with composition X equal to 1 and 75% for CCTO with X equal to 1.5 and 85% for CCTO X equal to 2. Then kinetic study was also carried out using Langmuir-Hinshelwood kinetic equation. PL study was also carried out for the material, where we have found that the material has some broad and asymmetric peak, which is due to the reason of some defective origin. So in this comparison table, we have found that the composition with X equal to 1 has the better degradation percentage of 99.744% and has better degradation rate constant of 1.63 into 10 to the power minus 2 minute inverse, which is attributed due to its better defect density that was calculated through integral intensity method, which was 1.454. So to investigate the mechanism, various scavenger test was also carried out, where I have used isopropyl alcohol as a hydroxyl radical scavenger and parabenzoquinone as a superoxide radical scavenger, where we have found that while adding benzoquinone, the degradation process was suppressed. So in the degradation process, we can conclude that the main active species was the superoxide radical. So in conclusion, we have prepared calcium copper titanate, a cubic double perovskite, and its composition through citrate precursor method. The photocatalytic property of the material is examined through illumination of a 20-watt LED light. The kinetic study was also carried out, where we have found that the composition with X equal to 1 has the better higher weight constant of the reaction in comparison to other synthesized material. And the PL study was of the material was justified that the higher defect concentration and followed by better photocatalytic performance. So this work has been recently published in the Journal of Inorganic and Organometallics polymer and materials. So these are the references. In acknowledgement, I would like to acknowledge Tesco University for providing the institutional fellowship. I would also like to thank SIG Tesco University for providing analytical supports. I also like to acknowledge Organizing Committee of International Conference on Material Chemistry and Catalysis for giving me chance to present my work. So thank you.
Okay, thank you, Priyanka Mani, for the nice presentation. Now, if anyone has any doubts, they can just unmute themselves. Okay, I guess there are no questions. So thank you once again, Priyanka Mani. So next we have Mr. Devajyoti Nath from Department of Physics, Tripura University. So Mr. Devajyoti Nath, am I audible? Devajyoti Nath. Am I audible? No, I can't hear you. Kindly try to reconnect. Okay, have you logged in from two devices? There are two accounts which are appearing here. Try to connect from one device only. Okay, in the meantime, Devajyoti Nath tries to reconnect himself. We will move on to the next presentation. Next, we have Mr. Prasujapitram Udoy from Department of Chemical Sciences.
Hello, sir.
Yes.
Hello, sir.
Hello. Okay. Yes, I can hear you now. Devajyoti.
Hello, sir.
Yes, I can hear you. Yes. Kindly begin with the presentation, Mr. Devajyoti Nath.
Good evening, everyone. Am I audible, sir?
Yes. Please carry on.
Yeah. Good evening, everyone. I'm working in the Department of Physics, Tripura University as a research scholar. So I'm going to talk about microstructural characterization of chemically prepared CDSC nanocrystals through X-ray diffraction profile analysis. So firstly, materials in the range of 1 to 100 nanometer are known as nanoparticles. They actually show some special feature due to their high surface to volume ratio. Among these, semiconductor nanoparticles are very important due to their different technological application. Moreover, we have observed that semiconductor nanoparticles also show some quantum size effect, as per which size of the nanoparticle actually hugely influence other physical and chemical properties of the sample. Thus, the study of microstructural properties becomes very importance in the view of optoelectronic device applications. Here, actually, we have prepared the CDSC nanocrystals through a wet chemical method using selenium precursor and cadmium chloride. Morphological characterization of the prepared CDSC has been performed using SEM analysis, STEM analysis, and AFM. And moreover, microstructural characterization of the prepared CDSC has been performed using X-ray diffraction analysis based on the broadening of the diffraction peaks. So this figure actually shows the particle size along with the surface morphology of the prepared CDSC nanocrystal. Here it is clearly visible that particles are uniformly distributed with average particle size of around 36-37 nanometer. TEM also shows similar results. Figure A is the HRTEM image of the prepared CDSC. B is the size distribution from which we can get information about the average particle size. We have observed that the size of the TEM is also similar to the size of SEM that we have obtained, and the particle size is around roughly 38 nanometer. Further, we have observed that there are some dislocations in the prepared nanocrystal, which can also be characterized using peak broadening analysis. So this is the AFM image. This shows the this is the 3D CDSC surface image, which shows dense particles with significant uniformity, having average surface roughness of 3.6 nanometer. Now, microstructural characterization. The XRD profile of the chemical prepared CDSC nanocrystal has been taken in the range of 20 to 60 degree with step size of 0.02 degree. XRD pattern has been performed with incident radiation of 1.5406 angstrom. We have observed 4 diffraction peaks actually at 111 plane, 200 plane, 220 plane, and 311 plane. The pattern that we have obtained is actually matches very well with the standard GCP card number, which confirms the cubic lattice geometry of the prepared sample. Further, we have seen that the diffraction peaks in the figure. We have seen that the diffraction peak actually start to broaden with due to some physical properties. Here we have corrected the physical broadening based on the instrumental broadening part, and we have obtained the broadening as beta square equal to beta d square minus beta instrument square, where instrumental broadening has been corrected based on the crystalline silicon, which is used as a standard reference material. And from this broadening, we have used the XRD peak profile analysis to study the physical character of the sample. Now we have used the Sharer method. Sharer method actually consider only the crystallite size effect. Thus, we have obtained the average particle size where based on the broadening. So beta is equal to is actually the broadening part, and beta is equal to 0.9 lambda by d cos theta, where d is the average particle size and theta is for the planes where we have got the planes in the XRD pattern. So from this we have got the average particle size. Now Sharer equation actually only considers the size induced broadening. That's why we don't get any information about the microstructure of the lattice. That is the imperfection, that is the microstrain or point defect or grain boundary or stroking fault. Thus, we have considered the Williamson-Hall method. Williamson-Hall method actually considers the physical broadening as a combined effect of size-induced broadening as well as distortion-induced broadening, where the contribution of microstrain is assumed as this 4 epsilon 10 theta term. Thus, the total broadening is size-induced broadening plus strain-induced broadening. Now, we have considered 3 different models of the Williamson-Hall equation. First one is the uniform deformation model, where uniform deformation model considers the uniform strain throughout the crystallography direction, which gets introduced in the nanocrystal due to the crystal imperfection. Further, this is the amount of the strain which get introduced in the system during the synthesis of the nanocrystal. Thus, rearranging the equation and plotting the constant, we can get information about the average particles. Now, this is the second method. This is the uniform stress deformation model. Actually, what happened? UDM model considers the isotropic nature of the strain, but in the real crystal, isotropic nature is not strictly followed. That's why we have considered an anisotropic constant term, that is the term which has different values along the along all the plane direction. Thus, where we have used the Stokes law, that is stress is equal to strain into a Young's modulus. This stress is can be calculated if we get information about the y scale.
You have 2 minutes left.
Okay. Now this is the so from this we can get information about the stress. Now there is another model, UDEDM model. This model actually considers the the electron energy density as a function of the broadening. Thus, in both this model, we have used the isotropic nature of the strain, but here we use energy density as a function of the broadening. Thus, these are the result of all the model where we have got that the particle size of the UDOT model actually shows better results with the our morphology study. There is 7-term study. This work actually published in Materials Chemistry and Physics last year. Now we are doing another model. This is modified Williamson Hall model. Modified Williamson Hall model actually considers the anisotropic strain. That is, the strain component is directional dependent. Directional. That is, it will have different value and different direction. Where this strain is considered in terms of a parameter known as C. That is contrast factor. This contrast factor is direct function of 1 minus q h square. H square is directly dependent on HKL. Thus, if you can get information about the C, then you can get information about the average particle size as well as the other microstructure parameters. So from this, we plotted del k and kc to the power half. C is the anisotropic constant which is obtained from different way. You can get the information about the C. We have observed here. We have calculated this C from a program, an exact program. This is actually freely available. We have calculated C from this program, and then we got the average particle size. We found that the particle size get from this modified Williamson Hall method and the UDAT model shows better resemblance with the morphological study. Thus, in conclusion, we can say that if we consider UDAT model and the modified Williamson Hall model, then we can get better results for the microstructural characterization than this uniform strain distribution of the remaining system. So these are the reference, and thank you.
Thank you very much, Devajyoti. So if anyone has any queries, kindly unmute yourself and ask. Okay, I guess there are no questions. So thank you once again, Devajyoti.
Yes, thank you, sir.
Okay, now I move to the next presentation by Mr. Prasujya Pritam Udoy from Department of Chemical Sciences, Tezpur University.
Thank you so much. Very good evening to all of you. At the very first, I want to thank this organizing committee and the convener sir for giving me this opportunity in this intellectual gathering. So today I am going to talk about a part of my work. The title of my work is just protonation induced intramolecular metal charge transfer in a highly symmetric sine interface iron to nickel to molecular square. So the concept of single molecule magnetism has been started very early in 1993 by Dante and Peterson, and followed by lots of synthetic procedures have been adopted to modify these systems. So in that cases, cyanide is extensively used, and the versatility of the cyanide can be realized in terms of single molecule magnet, single chain magnet, spin crossover, photo-switchable magnet. So in this presentation, I will be stick to only photo-switchable magnet. So you can see that the photomagnetism has been started very early in 1996 by Hashimoto. They have actually reported three-dimensional iron cobalt structure, and where they have found that there can be switch of iron cobalt oxidation state by means of external stimuli. Here the external stimuli is light or temperature. So in that the journey comes from discrete from three-dimensional fragment to discrete molecular fragment. You can see that the first discrete molecular fragment has been it is a pentagonal vibration mineral complexes, then a cube, then square, and very recently in 2013 Rudolf Derek introduced a dinuclear iron cobalt complexes. So the mechanism in that case is that there is a switching of paramagnetic state of and diamagnetic state by means of temperature or light. So this is the whole mechanism where a high spin cobalt can be converted into cobalt low spin. So in that cases actually too many work has been done in cobalt ion systems. So there are very sporadic reports on other bimetallic systems. So you can see that there is a nice piece of work by Barbara Seitluka, and it was in Bangkok 2015, a chain of nickel iron complexes so stimuli responsive intramolecular electron transfer. So in that cases, here the stimuli is hydration. That means hydration rehydration can switch the oxidation state of nickel as well as iron, and it actually inspire us to do in our work. So in our cases, we have synthesized a square complexes of nickel iron by taking tribodal transcendental ligand and tricyanide BBP cyanide ligand, and it was actually characterized with all traditional or advanced structural and analytical spectroscopic designs. So, since lots of nickel iron complexes have also been reported in the literature, so we find what is anything interesting in the compound, and we look structurally or chemically, and we found what we have done that we have go for the measurement of this iron nickel bond distance and angle, and we found that after comparison with those reported iron nickel square complexes, that our system becomes more symmetric nature. So structurally it is important. Now we move for the chemical importance of our compound, and we record UV visible spectra. You can see that in the range of 620 there is a LMCT band which is attributed to the iron cyanide, and what we have done, we are now trying to find that protonation induced electron transfer in the compound, and thus we added trifluoroacetic acid in the compound. So you can see that there is a nice evolution of an MLCT band, and there is a disappearance of MLCT band in the compound, and also there is a change of color sense from dark blue to purple color in the compound. So you can see that this LMCT band has been reducing progressively, and there is a MLCT band progressively increases. So what we have done, in the next phases we have done normalized observance we taken, and we find that before one equivalent of point there is no significant modification, and similarly we observe in the MLCT band, and we found that there is the change is linear. Apart from that, we have looked about the ratio, that is the crossing point of the compound, and we found that it is below 0.5. That means it shows non-ratiometric evolution. That means LMCT band is disappearing and simultaneously MLCT band is appearing. In that cases, it actually provides us the report of protonation in these possible sites. Moving forward, we have actually estimated the fraction of the compound. You can see that at very particular state of one equivalent or two equivalent, there is one fraction is dominant, where iron is in iron 3 oxidation state and nickel is in nickel 2 oxidation state. Apart from this acid behavior, we also look about the possible protonation in case of base in the compound, and we say there is an evolution of LMCT band in the compound, but we do not observe any isobastic point. That means we do not have any control over this protonation or electron transfer in the compound. In order to support this observed phenomena, we have reported cyclic voltammetry of the compound, and we found that both oxidation peak for nickel as well as reduction peak for iron was observed in that cases. Now we have moved one step more, and we have added acid to the compound, and then took the cyclic voltammetry measurement, and we try to look that is there any sense of redox potential in the compound, and surprisingly we found that.
Sorry to interrupt, Pastorja, you have 2 minutes left.
Okay, thank you. Then there is a quite shift in the positive potential of the compound, which can be visualized like that. So the shifting actually reduces the redox potential defined of iron and the nickel side, and it eventually allows metal to metal electron transfer in the said complexes. With this, I come to the conclusion that we have prepared a square complexes. We dissolve in DMC solvent followed by acidification, and we can able to find there is a metal to metal electron transfer in the said compound. With this, I really I want to acknowledge my supervisor sir and all the faculty members of Department of Chemical Science and all who have supported during my work, and finally the organizing committee for giving me this platform. Thank you so much.
Okay, thank you, Prasurja, for the nice presentation.
Thank you.
So in case anyone has any queries, they may just unmute themselves and ask. So I guess there are no questions. So once again, thank you, Prasurja.
Thank you so much.
So we were left with one oral presentation yesterday of Miss Rajashree Bortamoli. She could not connect yesterday. So today she will be trying to present her oral presentation. So Rajashri Bhattamoli, you can just carry on with your presentation.
Okay.
So Rajashri, you can start sharing your slide.
Can you see my slides?
One second. Yes, your slides are visible, so kindly carry on.
Okay. Good evening, everyone. I am Rajashri Bhattamoli from Guwahati University. My topic of presentation is development of titanium-supported bio-derived carbon composite for utilization as supercapacitor electrode material. So let's begin. The demand for energy is ever increasing, and the fossil fuel depletion inflames the charge for sustainable energy storage system. So supercapacitor can be claimed as a potential candidate for it. So for what are supercapacitors? Supercapacitors are clean energy storage devices having specific power much higher than conventional batteries and specific energy much higher than normal capacitors. Supercapacitors have many advantages like long cycle life, high per unit mass capacitance, fast charge-discharge dynamics, good power and energy densities. So we have chosen titania for the electrode material preparation. Titania is an excellent choice because of its accessible electrochemically active surface and a high chemical stability. And activated carbons are also considered as electric double layer capacitance electrode material because of its high electrical conductivity, high surface area and controllable pore size. We have used bio-derived carbon because they have least impact on environment, are biodegradable, have low cost. We have synthesized bio-derived carbon from oleander seeds, and with that carbon we have prepared a nano composite with titania of varying composition 1:3, 1:10 and 1:100, but since the 1:3 composite is showing better results, so we are using that. So this is the procedure by which we have synthesized the composite. Then the electrode are prepared by mixing 80% of the active material, 10% activated carbon and 10% binder in the required amount of solution for 2 hours and coated onto the graphite sheet in 1:1 centimeter square dimension. So here are the results and discussion. We have done the Raman spectroscopy and XRD pattern spectroscopy. For the Raman, we have got that all the modes corresponds to the anatase titania. The G band of carbon is not visible clearly because of the masking effect of carbon, masking effect of titania. And in the XRD pattern also, all the planes corresponds to anatase titania except the peak at 27.6 corresponding to the plane 110. The same